So, here's something worth thinking about as you settle in tonight. The universe has rules. Not suggestions, not guidelines, not recommendations. Rules. Hard, absolute, unbreakable rules about what is and what is not allowed to happen. And the strangest part is that these rules don't tell you what you can do. They tell you what you cannot do. They are prohibitions. 4 of them. And every single thing that happens in the physical world, every cup of coffee that cools, every engine that burns fuel, every star that shines, every breath you take, every thought you think, happens inside the walls those 4 prohibitions create. You are living inside them right now. Right now, as you're lying there, your body is converting the chemical energy from whatever you had for dinner into thermal energy. And that thermal energy is radiating off your skin and into the air around you. You didn't choose to do that. You couldn't stop it if you tried. The second prohibition says the energy must spread out. It must. And it will keep spreading until the room around you is ever so slightly warmer and your body is ever so slightly cooler. And the difference between you and the room shrinks, fraction of a degree by fraction of a degree. You cannot reverse this process. You cannot gather up that scattered warmth and put it back into your body without paying a price somewhere else. The universe insists. And here is what most people never realize. These 4 rules, these 4 prohibitions, they weren't discovered all at once. They weren't even discovered in order. The one we call the zeroth law, the very first foundation, wasn't named until decades after the first and second laws were already established. It was so obvious that nobody thought to write it down, and then it turned out that without it, none of the others made sense. The whole thing had to be reorganized, like discovering that a building's foundation was poured after the second floor was already built. The people who figured these rules out were not working together. They were scattered across a century, across continents, across disciplines. A military engineer's son trying to restore France's glory after Napoleon's fall. A brewer from Manchester obsessed with measuring tiny temperature changes. A German doctor on a ship in the tropics who had a flash of insight that nobody believed. An Austrian physicist so tormented by the rejection of his ideas that he took his own life, only to be proven right a few years later. Their stories weave together into something extraordinary, a slow, century-long detective story about the deepest rules governing reality itself. And all of this raises questions that seem simple but turn out to be bottomless. Why does your coffee cool down but never heat back up? You've watched it happen 1,000 times. The mug sits on the table. The coffee gets colder. The room gets imperceptibly warmer. And never, not once, has the process reversed itself. The energy is all still there. Nothing has been lost. So what stops it from running backward? Why can't you build a machine that runs forever? People have tried for centuries, brilliant people, people who understood mechanics and geometry and leverage. They built wheels with shifting weights, chambers with flowing mercury, devices of extraordinary ingenuity. Every single one stopped. Why? What invisible wall are they hitting? Why does everything fall apart? Buildings crumble, iron rusts, mountains erode, your body ages. The most carefully maintained machine wears down. Why is decay the default? Why does the universe seem to favor disorder over order, ruin over structure, uniformity over complexity? And if it does, if the universe really is sliding toward featureless sameness, then how are you here? How is anything here? How does a universe that favors disorder produce galaxies and oceans and symphonies and the neurons firing in your brain right now? And the deepest question of all, why does time move in one direction? You can remember yesterday but not tomorrow. An egg breaks but never unbreaks. A candle burns but never unburns. The fundamental laws of physics, The equations that govern every particle in the universe work exactly the same way forward and backward. So where does the arrow come from? What gives time its direction? The answer to every one of those questions is the same: the 4 prohibitions. And tonight we are going to see exactly how. So tonight let's walk through all of it, the whole thing. From the very beginning, from the first confused attempts to understand what heat even is, all the way through to the final devastating implications for the fate of the universe. We'll take the 4 prohibitions one by one, in the order they actually make sense rather than the order they were discovered, and by the end, I think you'll see something surprising. These rules that seem so restrictive, these walls that box in what the universe can do, they are the very reason anything interesting happens at all. Without the prohibitions, there would be no structure, no complexity, no stars, no planets, no life. The walls of the maze are what create the path. And if you drift off somewhere along the way, that's perfectly fine. The universe will still be following its rules in the morning. There's no rush. Let's just settle in and talk about why things happen the way they do, and why they can never, ever happen any other way. But before we get to the 4 prohibitions themselves, we need to understand the world that existed before anyone knew the rules. Because for most of human history, people had no idea what heat was, where it came from, or where it went. And the story of how they figured it out starts, like so many things do, with a very practical problem and a very deep hole in the ground. For most of human history, heat was basically magic. Not literally, not in the sense that people thought wizards were involved, but in the sense that nobody had a satisfying mechanical explanation for what was actually happening when something got hot. You could feel it, you could use it. Blacksmiths could forge iron, cooks could roast meat, glassblowers could shape sand into vessels. The practical knowledge was enormous, passed down through generations of craftspeople who understood fire the way a sailor understands wind, intimately and intuitively, without needing to write a single equation. But if you had asked any of them what heat actually was, what was physically happening when a piece of metal glowed red in a forge, they couldn't have told you. Not really. And for thousands of years, nobody needed them to. Then something changed. Sometime in the late 1600s and into the 1700s, people in Britain started getting very, very interested in a specific problem. They needed to pump water out of mines, and that might sound mundane, almost boring, but think about what was happening in Britain at the time. The country was running on coal. Coal-heated homes, coal-powered early industries, and the demand was growing fast. The deeper you dig a coal mine, the more groundwater seeps in, and if you can't get the water out, you can't get the coal out. And if you can't get the coal out, everything grinds to a halt. So mine drainage wasn't just an engineering nuisance, it was an economic crisis in slow motion. For a while, they used horses. Teams of horses walking in circles, turning pumps, lifting water bucket by bucket. It worked, sort of, but it was expensive, slow, and the horses needed food, rest, and had an inconvenient tendency to eventually die. What people really wanted was a machine. Something that could pump water tirelessly, day and night, without eating oats or needing a veterinarian. Around 1698, an English military engineer named Thomas Savery patented a device he called the miner's friend. The idea was clever. You would heat water in a sealed vessel until it turned to steam, filling the chamber. Then you would cool the chamber by pouring cold water over it. The steam would condense back into liquid. And since liquid water takes up vastly less space than steam, roughly 1,600 times less volume, That condensation would create a partial vacuum inside the vessel, and that vacuum would suck water up from the mine below. Savory was using the atmosphere itself as his muscle. The weight of all that air above us, pressing down on everything at about 14.5 pounds per square inch. That air pressure would push water up into the vacuum that the condensing steam left behind. But Savory's engine had serious problems. The vacuum could only lift water about 30 feet, because that's the maximum column of water that atmospheric pressure can support. Mines were often much deeper. So Savory tried using pressurized steam to push water the rest of the way. But the boilers and vessels of his era couldn't handle high pressures safely. They leaked, they burst, the soldered joints failed. It was dangerous, unreliable, and while Savory deserves credit for the concept, his engine never really solved the mine drainage problem at scale. The person who did solve it, or at least got much closer, was Thomas Newcomen. Newcomen was a different kind of character entirely. He wasn't a gentleman inventor or a military engineer. He was an ironmonger from Dartmouth, a hardware dealer who sold tools to the mining industry. He knew miners. He knew their problems. He spent years of quiet, patient development on his own design. And sometime around 1712, he built an engine that actually worked. Newcomen's engine used the same basic principle as Savory's, steam condensation creating a vacuum, but with a crucial mechanical improvement. Instead of using the vacuum directly to suck up water, Newcomen used it to drive a piston inside a cylinder. Steam would fill the cylinder, pushing the piston up. Then a jet of cold water would spray into the cylinder, condensing the steam and creating a vacuum below the piston. The atmosphere would then push the piston back down. And that piston was connected through a big rocking beam to a pump down in the mine. Up, down, up, down. About 12 strokes a minute, slow and ponderous, the great beam rocking back and forth like a giant breathing. It was loud. It was inefficient. It consumed enormous quantities of coal. But it worked. It actually, reliably, continuously pumped water out of mines. And because the mines had coal right there, because you were literally sitting on top of the fuel supply, the inefficiency didn't matter as much as you might think. What mattered was that the water came out and the miners could keep digging. Newcomen's engine spread across Britain and then across Europe. By the middle of the 1700s, hundreds of them were nodding away at mine heads, and they became one of the defining technologies of the early industrial age. Now, here's what's fascinating from our perspective tonight. Nobody who built or operated these engines really understood why they worked. I mean, they understood the mechanics. Steam goes in, cold water condenses it, piston goes down. But the deeper questions, the ones that would eventually lead to the 4 prohibitions we're going to talk about, those questions were still wide open. What is heat, actually? What is happening to the energy when steam condenses? Why does it take so much coal to do so little useful work? Is there a limit to how much better these engines can get? Or could you, in principle, keep improving forever? Those questions hung in the air, unanswered, for decades. The machines existed before the science that explained them. Practice was far ahead of theory. People were harnessing the power of heat and steam through trial and error, through intuition and craftsmanship, and the theoretical framework was scrambling to catch up. And to understand why the theory was so slow in coming, you need to appreciate just how confused everyone was about heat itself. Because in the 1700s, the dominant explanation for heat was something called caloric theory. And caloric theory was beautiful, logical, intuitive, and almost entirely wrong. The idea was straightforward. Heat, according to caloric theory, was an actual physical substance, a weightless, invisible, self-repelling fluid called caloric that flowed from hot objects to cold ones. If you think about it, the metaphor makes sense. It really does seem like heat flows. You put a hot iron next to a cold one, and the hot one cools down while the cold one warms up, as if something is literally pouring from one to the other, the way water flows downhill. Antoine Lavoisier, the great French chemist, the same Lavoisier who figured out what oxygen was and who lost his head to the guillotine during the French Revolution, he was a major proponent of caloric theory. He thought caloric was a real element, as real as oxygen or hydrogen, just harder to detect because it had no weight. And caloric theory worked surprisingly well for a surprisingly long time. Heat flows from hot to cold, just like water flows from high to low. When you compress a gas, it gets hotter, because maybe you're squeezing the caloric out of it. When you mix hot and cold water, you get warm water, because the caloric is distributing itself evenly. It explained a lot of everyday observations, and it provided a coherent framework that physicians and engineers could use to think about thermal phenomena. It was neat. It was tidy. It made intuitive sense. But there were cracks. There were observations that didn't quite fit. And one of the most famous came from a truly unlikely source. Benjamin Thompson was born in Massachusetts in 1753. He spied for the British during the American Revolution. He fled to England, was knighted, moved to Bavaria, reorganized the Bavarian army, invented a more efficient fireplace, and founded the Royal Institution in London. One of the most colourful lives of the 18th century. And somewhere in between all of that, around 1798, he was overseeing the boring of brass cannons at a military arsenal in Munich. Boring, as in drilling out the barrel, was a process that generated enormous amounts of heat through friction. The brass shavings were hot, the cannon was hot, everything was hot. They had to keep pouring water over the apparatus to keep it cool. Now, under caloric theory, this heat was supposed to be caloric fluid being squeezed out of the brass as it was cut and ground away. But Thomson noticed something that didn't add up. The heat just kept coming. As long as the boring tool kept turning, heat kept being produced. It didn't matter how much brass had been removed. Even a dull tool, one that was barely cutting any metal at all, produced enormous amounts of heat. If caloric were a substance contained in the brass, you would expect it to run out eventually, like squeezing water from a sponge. But it never ran out. The supply of heat seemed inexhaustible as long as you kept doing mechanical work. Thomson concluded that heat could not be a material substance. It had to be something else, something related to motion. He wrote it up and published it, and his paper is one of those landmark documents in the history of science. He was right, fundamentally right, that heat is related to motion rather than being a fluid. But almost nobody listened, not right away. Caloric theory was too entrenched, too useful, too elegant in its own way. And Thomson himself, brilliant as he was, didn't provide a complete alternative. He poked a hole in the old idea without fully building the new one. So, as the 1700s turned into the 1800s, the situation was this. There were these incredible machines, steam engines, transforming the world. And there was this deep, unresolved question about what heat actually was and how it related to mechanical work. The engineers kept building bigger and better engines. The natural philosophers kept arguing about caloric. And somewhere in the gap between those two worlds, a science was waiting to be born. The person who would take the first truly decisive step. The person who would see the outline of the first prohibition was, improbably, a young French military engineer who published one slim book, was largely ignored during his lifetime, and died of cholera at the age of 36. His story is coming. But first, we need to lay the very foundation, the prohibition that is so obvious, so basic, so seemingly trivial, that it took over a century for anyone to bother writing it down. And yet, without it, none of the other three make any sense at all. I want to return to something we passed through quickly earlier because it deserves more space. Caloric theory. The idea that heat is a physical substance, a self-repelling, weightless fluid that flows from hot objects to cold ones. because understanding why caloric theory was wrong, and more importantly, why it was so compelling for so long, teaches you something deep about how science actually works, and about why thermodynamics was so hard to get right. Caloric theory wasn't stupid. It was, in many ways, a perfectly reasonable interpretation of the evidence available at the time. Think about your everyday experience of heat. When you pour hot water into a cold cup, the cup warms up and the water cools down. Something seems to flow from the water to the cup. When you put your hand on a warm stove, something flows into your hand and makes it hurt. When you mix hot and cold water, you get warm water, as if the caloric fluid from the hot water has spread out and mixed with the cold water. The caloric model handled all of this beautifully. Caloric was conserved, so the total amount stayed the same.
Caloric was self-repelling, which explained why heat spread out. Caloric particles pushed each other apart, seeking to distribute themselves as evenly as possible. Caloric flowed from hot to cold because hot objects had more caloric, and the self-repulsion pushed the excess toward the deficit. And caloric theory made testable predictions, several of which turned out to be correct. Joseph Black, a Scottish chemist working in the 1760s, used the caloric framework to develop the concepts of specific heat and latent heat. He showed that different substances require different amounts of caloric to raise their temperature by the same amount, which is specific heat. He showed that when ice melts, it absorbs caloric without changing temperature, which is latent heat. These concepts survive intact today, stripped of the caloric interpretation, but otherwise unchanged. Black's measurements were excellent. His framework was wrong in its mechanism, but right in its bookkeeping. Even Carnot, when he wrote his reflections on the motive power of fire in 1824, used caloric theory. He imagined caloric flowing from the hot reservoir through the engine to the cold reservoir, like water through a water wheel, and doing work as it dropped from high temperature to low temperature. His analogy was water falling from a height. The amount of work depends on the height of the fall, not on the amount of water. Similarly, the efficiency of the engine depends on the temperature difference, not on the amount of caloric. Carnot was wrong about the mechanism. Heat is not a conserved fluid flowing through the engine. Some of the heat is genuinely converted into work, and the heat coming out the cold side is less than the heat going in the hot side. But Carnot's conclusion about efficiency was right anyway, because the mathematical structure of his argument didn't depend on the conservation of caloric. It depended on the reversibility of the ideal cycle, which was a separate and valid insight. This is one of those cases where a scientist reaches the right conclusion through partially wrong reasoning, and history sorts out which parts to keep and which to discard. The death of caloric theory came slowly and was never the result of a single decisive experiment. Rumford's cannon-boring observation in 1798 was a serious challenge, but it wasn't lethal on its own. People could patch the theory by arguing that the act of drilling changed the capacity of the metal to hold caloric, that the shavings had a lower specific heat than the solid brass, so the caloric they released was less than it seemed. The patches were awkward, but they worked well enough to keep the theory alive. It was Joule's careful, repeated measurements in the 1840s and 50s that finally made caloric untenable. Joule showed that mechanical work and heat are interconvertible with a precise, universal exchange rate. If heat were a conserved fluid, you couldn't create it from scratch through mechanical work. But Joule showed that you could, repeatedly, with different apparatus, always getting the same conversion factor. The fluid model couldn't survive this. And yet, even after Joule's work, caloric language persisted. People still talked about heat flow and heat capacity and latent heat, as if heat were a thing that flowed and was stored. We still use those words today. The language of caloric theory is embedded in the vocabulary of modern thermodynamics.
even though the underlying physics has been completely replaced. When you say, the soup contains a lot of heat, you are speaking caloric. The correct thermodynamic statement would be, the soup has a high internal energy, or the soup is at a high temperature. Heat is a process, not a thing.
But the caloric language is so intuitive, so natural, that it refuses to die. And there is a lesson in this for anyone trying to understand thermodynamics. The everyday language of heat is caloric language, and it will mislead you if you take it literally. When your textbook says, heat flows from hot to cold, it does not mean there is a substance flowing. It means energy is being transferred because of a temperature difference. When it says, the system absorbs heat, it does not mean the system is soaking up a fluid. It means energy is entering the system through thermal contact. The precise, careful language of thermodynamics exists precisely because the everyday language is a trap. A beautiful, intuitive, wrong model inherited from 2 centuries ago. Keeping this distinction in mind, the distinction between the caloric intuition and the thermodynamic reality will save you from almost every common misconception in the subject. Heat is a process. Energy is a state.
Temperature is a property. Entropy is a measure of dispersal, and the 4 prohibitions govern how all of these relate to each other. And with caloric safely buried, we can now lay the true foundation. Because before we can talk about energy conservation, before we can talk about entropy and the arrow of time, we need something even more basic. We need to know that temperature itself is a real, consistent, trustworthy quantity. And proving that turns out to require a law so obvious that nobody bothered to write it down for over a century. Here is a statement that might strike you as almost insultingly obvious. If you put a hot object and a cold object in contact with each other, eventually they will reach the same temperature. The hot one cools down, the cold one warms up, and after enough time, they settle at some intermediate temperature and just stay there, neither one getting hotter, neither one getting cooler. They have reached what physicists call thermal equilibrium. You knew that already. Everyone knows that. Your coffee gets cold, your ice cream melts. The bathwater that was too hot when you ran it is perfect 20 minutes later. Thermal equilibrium is one of those things that is so woven into daily experience that it barely seems worth mentioning, let alone elevating to the status of a fundamental law of nature. And yet, there is a version of this idea that is not obvious at all, that is in fact quite subtle, and that turns out to be absolutely essential for the entire structure of thermodynamics to hold together. It goes like this. Suppose you have 3 objects. Call them A, B, and C. You check, and A is in thermal equilibrium with C. They are the same temperature. Then, separately, you check, and B is also in thermal equilibrium with C. B and C are the same temperature too. Now the question is, without bringing A and B into direct contact with each other, can you conclude that A and B are also in thermal equilibrium? That they are at the same temperature? Your immediate reaction is probably, well, obviously yes. If A equals C and B equals C, then A equals B. That's just basic logic, right? Like saying, if this stick is the same length as that ruler, and that other stick is also the same length as the ruler, then the 2 sticks are the same length as each other. It is so obvious it almost hurts to state it. But here is where things get interesting. In mathematics, this kind of property has a name. It is called transitivity. If A has the same relationship to C that B has to C, then A has the same relationship to B. And while transitivity holds for things like length and weight and many other physical properties, it does not hold for everything. There are relationships in mathematics and in physics that are not transitive. Just because A has a certain relationship with C and B has the same relationship with C does not always mean A has that relationship with B. So the fact that thermal equilibrium is transitive that it does obey this logical structure is actually saying something real about the physical world. It is saying something about the nature of temperature itself. Because if thermal equilibrium were not transitive, the whole concept of temperature would fall apart. You couldn't build a thermometer. Think about what a thermometer does. You put a thermometer in contact with some object, you wait for the thermometer and the object to reach thermal equilibrium, and then you read the thermometer. You are using the thermometer as a go-between, as object C in our ABC scenario. You are assuming, relying on the fact, that if the thermometer reads the same number for object A as it does for object B, then A and B must be at the same temperature as each other. Without transitivity, that assumption fails. Without transitivity, the thermometer reading for A tells you nothing about A's relationship with B. The whole enterprise of measuring temperature depends on this one seemingly trivial property. Now, you might be wondering why anyone needed to state this as a formal law. Hasn't it always been assumed? Hasn't every physicist since Galileo taken it for granted? And the answer is yes, basically, they did. For a very long time. The first and second laws of thermodynamics were formulated in the 1850s, refined over the following decades, and became cornerstones of physics. The third law came along around 1900, and it wasn't until the 1930s that a British physicist named Ralph Fowler looked at the whole structure and said, wait, there is an assumption buried underneath all of this that we never made explicit. We are assuming thermal equilibrium is transitive. We are assuming that temperature is a well-defined, consistent quantity that means the same thing when measured by any thermometer, applied to any object, in any context. And we never actually stated that as an axiom. Fowler's reaction was essentially the same as mine when I explained this. He thought it was so basic, so fundamental, so logically prior to everything else, that it needed to come before the first law. But the first law was already called the first law, and the second law was already called the second law. What do you call something that comes before the first? You call it the zeroth. The zeroth law of thermodynamics. And I love this detail because it tells you something about how science actually works. It is messy. The logical order and the historical order are almost never the same. People don't discover things in a neat sequence. They stumble into the deep truths and then spend decades rearranging the furniture to make everything look tidy. The zeroth law is the foundation of the building, but it was poured decades after the upper floors were already occupied. There is an analogy I have heard that I think captures this beautifully. Euclid, the ancient Greek mathematician, built his entire geometry on a set of axioms. And one of those axioms says, in essence, that a right angle is equal to every other right angle. Now, if someone told you that today, you might laugh. Of course, a right angle equals another right angle. 90 degrees is 90 degrees. What is there to state? But Euclid understood something profound. He understood that if you don't explicitly state your foundational assumptions, the entire structure built on top of them is resting on air. You might feel confident that it is solid, but you haven't actually checked. And that is exactly what happened with thermodynamics. For nearly a century, the entire science rested on an unstated assumption about the nature of temperature. The zeroth law made it explicit, and once it was explicit, the logical structure became clean. Temperature exists. It is measurable. It is consistent. Two objects in thermal equilibrium with a third are in thermal equilibrium with each other. From this foundation, everything else can be built. So that is the zeroth prohibition. And I want to frame it as a prohibition because even though it doesn't sound restrictive the way the other laws do, it is, in its own quiet way, telling the universe what it must do. It says, you must reach equilibrium. If two objects are in thermal contact, you cannot have a situation where A is in equilibrium with C and B is in equilibrium with C, but A and B are somehow at different temperatures. The universe doesn't allow that. Temperature must be consistent. Thermal equilibrium must be transitive. Put differently, the zeroth prohibition says there are no special relationships. Heat doesn't play favorites. If you are the same temperature as the thermometer and the soup is the same temperature as the thermometer, then you and the soup are the same temperature. No exceptions, no backdoors, no special cases. The universe insists on consistency. Now, you might think this is a rather gentle prohibition, and you are right. Compared to what is coming next, the zeroth law is the universe clearing its throat before delivering the real speech. Because the zeroth law tells you that temperature exists and that thermal equilibrium is real. But it says nothing about where energy comes from, where it goes, or why things change. For that, you need the first prohibition. And the first prohibition is going to require us to travel to a place nobody expected great physics to come from. A brewery in Salford, near Manchester, England, where a quiet, obsessive, meticulous man was about to prove something about the universe that would change everything. We spent time on the zeroth prohibition, on the transitivity of thermal equilibrium, and on how temperature is defined through that transitivity. But I want to push a bit deeper, because temperature itself, this quantity we think we understand so well, the number on the thermometer, the thing we check before deciding whether to wear a jacket, is considerably stranger than it appears. Start with this. Temperature is not the same as heat. This trips up nearly everyone at some point. A bathtub full of warm water contains far more thermal energy, far more internal energy, than a single spark from a sparkler. But the spark is at a much higher temperature. Temperature measures the intensity of thermal motion, the average kinetic energy per molecule, not the total amount of energy. A spark has very few molecules, but each one is moving very fast. A bathtub has an enormous number of molecules, each one moving relatively slowly. The spark can't hurt you much because it carries so little total energy, despite its high temperature. The bathtub can warm you because it carries so much total energy, despite its modest temperature. This is why you can walk through a sauna at 90 degrees Celsius without burning your skin, but touching water at 90 degrees Celsius would be catastrophic. The air in the sauna is at the same temperature as the water, but air is far less dense than water, so it carries far less energy per unit volume, and it transfers that energy to your skin far more slowly. The rate of energy transfer depends not only on the temperature difference, but also on the properties of the medium, its density, its specific heat, its thermal conductivity. Temperature alone doesn't determine whether something will burn you, and there is a deeper subtlety. We said temperature measures the average kinetic energy per molecule, but average is doing a lot of work in that sentence. In a gas at a given temperature, the molecules are not all moving at the same speed. Some are moving fast, some slowly, and most are somewhere in the middle. The distribution of speeds follows a specific mathematical curve called the Maxwell-Boltzmann distribution, and the shape of that curve depends on the temperature and the mass of the molecules. At higher temperatures, the distribution shifts toward higher speeds and broadens. At lower temperatures, it narrows and shifts toward lower speeds. So when we say a gas is at 300 Kelvin, we don't mean every molecule has the same kinetic energy. We mean the average is a certain value, and the distribution around that average has a specific, predictable shape. Temperature is a statistical quantity. It only makes sense when applied to a large collection of particles. You cannot meaningfully assign a temperature to a single atom. A single atom just has a kinetic energy. Temperature emerges from the collective behavior of many particles, from the statistics, from the averaging. This is connected to something we mentioned earlier, the idea that thermodynamics deals with macroscopic quantities. Temperature, pressure, volume, entropy, these are all properties of systems with vast numbers of particles. They don't apply to individual atoms or molecules. They are emergent properties, patterns that arise from the collective behavior of many particles, patterns that are extraordinarily robust and reliable, precisely because the numbers involved are so enormous. When you have 10 to the 23rd particles, the statistical fluctuations are so tiny relative to the average that the macroscopic quantities are, for all practical purposes, perfectly smooth, perfectly predictable, perfectly law-abiding. The zeroth prohibition, the transitivity of thermal equilibrium, is a macroscopic law. It holds because of the statistics. If you had a gas of only 5 particles, thermal equilibrium would fluctuate wildly. Temperatures would bounce around. The concept of equilibrium would be fuzzy and unreliable. But with Avogadro's number of particles, about 6 times 10 to the 23rd, the fluctuations are negligibly small, and the zeroth prohibition holds with rock-solid reliability. This is a recurring theme in thermodynamics. The laws are statistical. They hold because of the enormous numbers involved. In principle, they could be violated. A cup of coffee could spontaneously heat up. Entropy could decrease. Heat could flow from cold to hot. In principle. But the probabilities are so absurdly small that these events will never occur in the lifetime of the universe. The laws of thermodynamics are not logical necessities. They are practical certainties. And the distinction matters because it reveals the deep connection between thermodynamics and probability, between the macroscopic world of engines and temperatures and the microscopic world of atoms and statistics. Boltzmann saw this connection, and it cost him everything. But the vision he left behind, the vision of a bridge between two worlds, between the thermodynamic and the statistical, is one of the great intellectual achievements of human history. His formula, S equals K log W, is the keystone of that bridge. And every time you check the temperature on a thermometer, every time you feel the warmth of a cup of coffee, every time you notice that your ice cream has melted, you are witnessing the consequences of that formula, the macroscopic manifestations of microscopic statistics, playing out exactly as Boltzmann predicted. The first prohibition is the one you probably already know, even if you have never heard it called a prohibition. It says, energy cannot be created, and it cannot be destroyed. It can only be converted from one form to another. The total energy of a closed system, or of the universe as a whole, remains constant. Always. Without exception. You can turn chemical energy into heat. You can turn heat into mechanical work. You can turn mechanical work into electrical energy. You can turn electrical energy into light. But at every step, the total amount stays the same. Nothing is gained, nothing is lost. The books always balance. You can rearrange energy. You can move it around. You can dress it up in different forms. But you can never, ever make more of it. And you can never, ever make less. This is the first law of thermodynamics. And stated so simply, it sounds almost self-evident, like the kind of thing you might shrug at and say, well, yes, obviously. But getting to this statement took over a century of confusion, argument, wrong turns, personal tragedy, and some of the most painstaking experimental work in the history of science. And the reason it took so long is that the first law is really two ideas glued together, and people had to discover both ideas separately before they could see the connection. The first idea is that heat and mechanical work are the same kind of thing. They are both forms of energy, and one can be converted into the other. This sounds simple now, but in the 1800s, it was genuinely revolutionary. Under caloric theory, heat was a substance. Work was a force applied over a distance. The idea that these two things were really the same thing, measured in the same units, interconvertible, that idea had to be fought for. The second idea is that this conversion is exact, that there is a precise, fixed, universal exchange rate between heat and work. That one unit of work always produces the same amount of heat, no matter how you do the conversion, no matter what apparatus you use, no matter where you are on the planet. The existence of this precise exchange rate, what we now call the mechanical equivalent of heat, is what makes the first law a quantitative law, rather than a vague philosophical principle. And proving that this exchange rate exists, measuring it, convincing the world that it was real, that was the life's work of a man named James Prescott Joule. But Joule wasn't first. There is another man who saw the same truth earlier, who wrote about it with genuine insight and clarity, and whose story is one of the saddest in the history of science. His name was Julius Robert von Mayer, and his flash of insight came not in a laboratory but on a ship. In 1840, Mayer was a 25-year-old German physician serving as a ship's doctor on a merchant vessel sailing to the Dutch East Indies, present-day Indonesia. While the ship was in the tropics, Mayer performed routine bloodlettings on the sailors, which was standard medical practice at the time, and he noticed something strange. The venous blood of the sailors in the tropics was unusually bright red, much redder than what he was accustomed to seeing in patients in Germany. Now Mayer knew that the difference in color between arterial blood, which is bright red, and venous blood, which is darker, comes from the difference in oxygen content. Arterial blood is rich in oxygen. Venous blood has given up some of its oxygen to the body's tissues. But in the tropics, even the venous blood looked surprisingly oxygenated. Why? Mayer thought about it, and he came up with an explanation that was, in hindsight, a stroke of genuine brilliance. In a hot climate, the body doesn't need to burn as much fuel to maintain its temperature. The environment is already warm, so the body uses less oxygen because less oxidation is needed for internal heating. The blood returns to the veins with more of its oxygen still intact. And then Mayer took the next step, the step that connected physiology to physics. He reasoned that the body's heat comes from a chemical process, the oxidation of food. That heat is a form of energy. That mechanical work is also a form of energy. And that these different forms, chemical, thermal, mechanical, are all interconvertible. They are all manifestations of a single underlying quantity that is conserved, that never increases or decreases, that merely changes form. He had, in essence, conceived of the conservation of energy while watching blood flow on a ship in the Java Sea. Mayer went home and tried to publish his ideas, and this is where his story gets painful. His first paper, submitted to a physics journal in 1841, was rejected. He wasn't a physicist, he was a doctor. His paper lacked mathematical rigor. The editors didn't know what to do with it. He eventually published a version in a chemistry journal in 1842, but it was largely ignored by the physics community. He tried to calculate the mechanical equivalent of heat from existing data on the specific heats of gases, and he got a remarkably good estimate. But his methods were theoretical rather than experimental, and the physics establishment of the time wanted experiments, they wanted measurements, they wanted data. Mayer had an idea. What he needed was a laboratory. He never got one. Over the following years, Mayer became increasingly frustrated and isolated. Other scientists published similar ideas without acknowledging his work. Priority disputes arose, particularly with Joule in England. Mayer felt robbed. In 1850, 2 of his children died. The combination of grief and professional rejection broke him. He attempted suicide by jumping from a 3rd-floor window, survived, and was committed to a psychiatric institution. He spent years in asylums, was subjected to brutal treatments, and was largely forgotten by the scientific world. Mayer did eventually recover, and in his later years, his contributions were recognized belatedly. He received honors including the Prix Poncelet from the French Academy of Sciences, but by then, the credit for establishing the first law had largely gone to others. Mayer's story is a reminder that in science, having the right idea at the right time is not enough. You also need the right credentials, the right connections, and the right kind of evidence. And sometimes, being right is the loneliest thing in the world. The person who did provide the right kind of evidence, the person whose name is now inseparable from the first law, was James Prescott Joule, and his story is everything that Mayer's was not. Where Mayer was a doctor and an outsider to physics, Joule came from a family that owned a brewery in Salford, near Manchester. He had resources, a workshop, and an almost pathological obsession with measuring things precisely. Joule wanted to know exactly how much mechanical work it took to raise the temperature of water by 1 degree. Think about what that question means. If heat is truly a form of energy, and if energy is truly conserved, then there should be a fixed, universal conversion rate. 1 unit of mechanical work should always produce the same amount of heat, no matter how you do it. Joule set out to prove this, and he did it through a series of experiments that are almost comically painstaking in their care and repetition. The most famous one involved a falling weight connected by a string and pulley to a paddle wheel submerged in an insulated container of water. The weight falls, the paddle turns, the water gets stirred, and the friction of the stirring heats the water. Joule measured the distance the weight fell and the tiny temperature increase in the water with extraordinary precision. We are talking about fractions of a degree Fahrenheit. He did this over and over and over. He tried different methods too, squeezing air, forcing water through narrow tubes, using electrical currents. And every single method gave him essentially the same conversion factor. A specific amount of mechanical work always produced the same amount of heat. He first presented his results in 1843, and again, more definitively, in 1845 and 1847. And like Carnot before him, and like Mayer around the same time, he was largely ignored at first. The scientific establishment was skeptical. Here was this brewer from Manchester, not a university man, claiming to have established a fundamental law of nature with homemade apparatus. When he presented his paddle wheel results at a meeting of the British Association for the Advancement of Science in 1847, the chairman reportedly suggested he give just a brief verbal summary so they could move on to other business. But someone in that audience was paying attention. A young man, just 23 years old, named William Thomson, the future Lord Kelvin. Thomson was intrigued, partly because he had recently been reading about Carnot's work on heat engines, which we will get to shortly, and he could sense that Joule's experimental findings and Carnot's theoretical insights were connected. But they also seemed to contradict each other in a troubling way, and that contradiction was going to take another brilliant mind to resolve. Let me pause here for a moment and make sure the picture is clear. By the late 1840s, the situation was roughly this. Rumford had shown 50 years earlier that heat could be produced from friction without limit, which strongly suggested heat was not a conserved fluid. Mayer had argued, on theoretical grounds, that heat and work were interconvertible forms of a single conserved quantity. And Joule had demonstrated, experimentally and repeatedly, that there was a precise numerical exchange rate between mechanical work and heat. The first law was taking shape. But it still needed someone to state it clearly, to extract it from the confusion, to reconcile it with what was already known about heat engines, and to present it as a clean, general, universal principle. That person was Rudolf Clausius. And Clausius was also the person who would go on to discover the second prohibition, the one that makes the first law look gentle by comparison. Clausius was born in 1822 in Köslin, a small town in what was then the Prussian province of Pomerania. He was the son of a pastor and school principal, quiet, methodical, the kind of thinker who could hold multiple contradictory ideas in his head without flinching, and wait, patiently, until he saw how they fit together. He studied at the University of Berlin, worked under some of the best physicists in Germany, and by his late 20s, he was ready to perform what might be the most elegant act of intellectual surgery in the history of physics. In 1850, Clausius published a paper that effectively created thermodynamics as a unified science. Its title translates roughly as "On the Moving Force of Heat and the Laws which may be deduced therefrom." And what he did in that paper was something nobody else had managed. He showed that Carnot was right about engine efficiency, that Joule was right about the interconvertibility of heat and work, and that caloric theory was wrong. All three of those statements could be true simultaneously, and here is how. Carnot had shown that you cannot convert heat into work without having a temperature difference. You need a hot source and a cold sink. The efficiency of an engine depends on that temperature gap. That result was correct, and Clausius kept it. What Carnot had also assumed, following caloric theory, was that the total amount of heat was conserved, that the heat flowing into the engine equaled the heat flowing out, like water through a mill wheel.
That part was wrong, and Clausius threw it out. Clausius replaced it with a simple, beautiful insight. Some of the heat that flows in from the hot source is genuinely converted into work. It doesn't come out the other side. The heat that does come out at the cold end is less than what went in, and the difference is exactly the work the engine performed. Energy is conserved, but heat is not. Heat can be created from work, and work can be created from heat, and the exchange rate between them is exactly what Joule measured. And in doing this, Clausius essentially stated the first law of thermodynamics in a clear, general form. Energy is conserved. It can change forms. Heat can become work. Work can become heat. But the total amount of energy in a closed system stays the same. If we write this in the language of thermodynamics, we say that the change in internal energy of a system, which we call delta U, equals the heat added to the system, which we call Q, plus the work done on the system, which we call W. Delta U equals Q plus W. That's it. That's the first law, written as a formula. Every problem in basic thermodynamics starts with this equation. Every analysis of a system, whether it's a steam engine, a refrigerator, a power plant, or the chemical reactions in your body, begins by asking how much heat came in, how much work was done, and what happened to the internal energy. Now, there are some subtleties in that formula that trip people up, and since we're taking our time tonight, let's talk about them. Because the sign conventions alone have caused more confusion in thermodynamics classrooms than almost any other single issue. When we say work done on the system, we mean work that the surroundings do on the system. If you compress a gas by pushing a piston inward, you are doing work on the gas. The gas's internal energy goes up. That makes the work positive in our convention. But if the gas expands and pushes the piston outward, the gas is doing work on the surroundings. From the gas's perspective, it is losing energy. So the work done on the system is negative, because the system is doing the work rather than receiving it. Similarly, heat added to the system is positive. Heat leaving the system is negative. And the internal energy change, delta U, just tells you the net result. If you add a lot of heat but the system also does a lot of work, the internal energy might barely change at all. The books still balance. Energy in minus energy out equals the change inside. Let me give you a simple example, the kind that appears in every thermodynamics textbook, but is worth walking through slowly. Imagine you have a gas in a cylinder with a piston. The gas starts at some temperature and pressure. Now you heat the gas. What happens? The gas gets hotter, its pressure increases, and it pushes the piston outward. The gas expands. You added heat to the system, so Q is positive. The gas did work by pushing the piston, so the work done on the system is negative because the system did the work rather than receiving it. The change in internal energy depends on the balance. If you added more heat than the gas spent doing work, the internal energy goes up. If the gas spent more energy pushing the piston than it received from the heating, the internal energy goes down. And if the process happens at constant temperature, if it is isothermal, then the internal energy doesn't change at all, because for an ideal gas,
internal energy depends only on temperature. In that case, all the heat you add goes directly into work done by the gas, and the equation becomes Q equals negative W, or equivalently, the heat in equals the work out. Nothing is stored, everything flows through. This is the kind of reasoning that makes thermodynamics so powerful. You don't need to know the details of what's happening inside the gas, the individual molecules bouncing around, the quantum mechanical vibrations. You just need the accounting. Energy in, energy out, change in storage. The first law handles the rest. But the first law also has a profound limitation, and recognizing that limitation is what led to the second prohibition, the one that Clausius himself would name and define. Because the first law tells you that energy is conserved. It tells you the books must balance. But it says absolutely nothing about which way the energy flows. Think about it. If I told you that a hot cup of coffee transferred heat to a cold room and reached thermal equilibrium, you would say, yes, that makes sense, and the first law is satisfied, because the energy lost by the coffee equals the energy gained by the room. The total stays constant. Books balanced. But now suppose I told you that a cold room spontaneously transferred heat to a warm cup of coffee, making the coffee hotter and the room colder, and the energy lost by the room equals the energy gained by the coffee. The books still balance. The first law is still satisfied. Energy is still conserved. And yet you know, instinctively, immediately, that this doesn't happen. Coffee doesn't spontaneously heat up by drawing warmth from a colder room. It never has. It never will. The first law doesn't explain why. The first law says the energy balance has to work out, and it does work out in both scenarios. Something else is needed, some other prohibition. A rule that doesn't just say how much, but says which way. A rule that distinguishes what can happen from what cannot, even when both options conserve energy perfectly. We will get to that second prohibition soon, and its discovery will take us to revolutionary France and a young man who wanted to save his country. But before we leave the first law behind, I want to make sure we've cleared up every piece of confusion it tends to cause. Because the sign conventions, the vocabulary, the distinction between heat and work and internal energy, these trip up almost everyone who encounters thermodynamics for the first time. And once they are clear, everything that follows becomes much easier. I want to stay with the first prohibition for a while longer, because there are aspects of it that confuse almost everyone who encounters thermodynamics for the first time, and I think the confusion is usually not about the physics. The physics is straightforward. The confusion is about the bookkeeping, about the conventions, about the way scientists decided to keep track of energy flowing in and out. And once you see why those conventions exist, the confusion evaporates. Let's start with the most fundamental question. What is internal energy? Internal energy is the total energy stored inside a system, all of it. The kinetic energy of every molecule bouncing around, the potential energy of the forces between molecules, the energy stored in the vibrations of molecular bonds, the rotational energy of molecules spinning. All of it summed up is the internal energy, usually written as U. Now, there are two things you cannot do with internal energy. You cannot measure its absolute value, and you don't need to. What matters in thermodynamics is never the total amount of internal energy, but the change. Delta U. How much did the internal energy go up or down during a process? That change is what the first law tracks. And there are exactly two ways to change the internal energy of a system. You can transfer heat, or you can do work. That's it. There are no other options. Every process that changes the internal energy of a system does so through some combination of heat and work. Heat, in thermodynamics, has a very specific meaning that is different from everyday usage. In everyday language, people say things like, "Close the door, you're letting the heat out," as if heat were a substance that could leak through a doorway. In thermodynamics, heat is not a substance. Heat is a process. It is the transfer of energy driven by a temperature difference. When a hot object is in contact with a cold one, energy flows from hot to cold, and that flow is what we call heat. Once the energy has been transferred, it is no longer heat. It is just energy, internal energy of the receiving object. Heat is the act of transfer, not the thing transferred. This is worth repeating because it is the source of enormous confusion. Heat is not something a system contains. A system contains internal energy. Heat is what happens when internal energy moves from one system to another because of a temperature difference. Asking, "How much heat does this object contain?" is like asking, "How much throwing does this baseball contain?" Throwing is something you do to a baseball, not something stored inside it. Work is the other way to change internal energy, and in thermodynamics, work usually means pressure-volume work. When a gas expands against a piston, the gas does work on the piston. The gas pushes the piston outward, moving it through a distance, and force times distance is work. The formula is W equals the integral of pressure times the change in volume, but for our purposes tonight, the important thing is the concept, not the calculus. When a gas expands, it does work on the surroundings. It spends some of its internal energy to push the piston. When a gas is compressed, the surroundings do work on the gas. The piston pushes inward, adding energy to the gas. Expansion means the gas loses energy through work. Compression means the gas gains energy through work. And here is where the sign conventions enter, and where people's eyes start to glaze over. In the convention used in most chemistry textbooks, work done on the system is positive, and work done by the system is negative. Heat added to the system is positive, and heat removed from the system is negative. Delta U equals Q plus W. If you add heat and do work on the system, both are positive, and the internal energy goes up. If the system loses heat and does work on its surroundings, both are negative, and the internal energy goes down. In many physics textbooks, the convention is slightly different. Work done by the system is positive, and the first law is written as delta U equals Q minus W. The physics is identical. The accounting is the same. It is purely a matter of which direction you define as positive for work. But switching between books that use different conventions can be maddening if you don't realize what's happening. The way I think about it is this. Imagine the system is a bank account. Deposits are positive, withdrawals are negative. Heat flowing in is a deposit. Heat flowing out is a withdrawal. Work done on the system is a deposit because someone is putting energy into your account. Work done by the system is a withdrawal because your system is spending energy. Delta U is the net change in your balance. The first law just says your balance changes by exactly the amount you deposited minus the amount you withdrew. No more, no less. No mysterious gains, no unexplained losses. The books always balance. Let me walk through a few scenarios to make this concrete. Scenario 1. You have a gas in an insulated container, a container that doesn't let any heat in or out. This is an adiabatic process. Q equals 0. Now you compress the gas by pushing the piston inward. You are doing work on the system, so W is positive. Delta U equals 0 plus W, which is positive. The internal energy goes up. The gas gets hotter. You put energy in through work, and since no heat can escape, all of that energy stays in the gas as internal energy, which means the temperature rises. This is exactly what happens in a diesel engine, by the way. Air is compressed so rapidly and so dramatically that it heats up to the point where diesel fuel ignites spontaneously when injected into the cylinder. No spark plug needed. The compression itself generates enough heat to ignite the fuel. That is the first law in action. Work done on the gas increases its internal energy, raising its temperature. Scenario 2. You have a gas in a container with thin metal walls, sitting in a large water bath that maintains a constant temperature. This is an isothermal process. The temperature doesn't change, so for an ideal gas, the internal energy doesn't change. Delta U equals 0. Now you let the gas expand slowly by pulling the piston outward. The gas does work on the piston, so W is negative. But delta U is 0, so Q must be positive and equal in magnitude to W. Heat flows into the gas from the water bath, replacing exactly the energy that the gas spent doing work. The gas absorbs heat and converts it entirely into work, with no change in internal energy. This might sound like it violates the second prohibition, since we seem to be converting heat entirely into work. But we are not running a cycle. We are doing a one-time expansion. The gas has changed state. It now occupies a larger volume, and to return it to its original state, we would have to compress it, doing work on it, which would require dumping heat back into the water bath. The second prohibition only says you can't convert heat entirely into work in a cyclic process, one that returns to its starting point. A one-time expansion is not a cycle. Scenario 3. You have a rigid, sealed container that can't expand or contract. The volume is fixed. This is an isochoric process. Since the volume doesn't change, no pressure-volume work is done. W equals 0. You heat the gas by placing the container over a flame. Q is positive. Delta U equals Q. All the heat goes into increasing the internal energy, which means the temperature rises and, in a rigid container, the pressure rises too. This is close to what happens in a bomb calorimeter, a device used in chemistry to measure the energy content of fuels and foods. You burn a sample inside a sealed, rigid container surrounded by water, measure how much the water temperature rises, and from that, you can calculate the change in internal energy of the combustion reaction. Because the volume is constant, no PV work is done, and all the energy released by the reaction goes into heating the water. Delta U equals Q at constant volume, and this brings us to a distinction that confuses many students, but is actually quite logical once you see the reason for it. In chemistry, most reactions happen at constant pressure, not constant volume. They happen in open beakers, in flasks, in living organisms, all of which are at atmospheric pressure. And when a reaction happens at constant pressure, the heat exchanged is not equal to delta U. It is equal to delta H, the change in enthalpy. Enthalpy, as we discussed, is defined as H equals U plus PV. The change in enthalpy is delta H equals delta U plus delta PV. At constant pressure, delta PV equals P times delta V, which is just the work done by the gas at constant pressure. So delta H equals delta U plus P delta V, which, using the first law, simplifies to delta H equals Q at constant pressure. The reason enthalpy exists as a separate quantity, the reason chemists bother defining H equals U plus PV, is entirely practical. It makes the bookkeeping easier for constant pressure processes. When you look up the heat of reaction in a chemistry table, you are almost always looking at delta H, not delta U. When a nutritionist says a food contains a certain number of calories, they are talking about enthalpy, not internal energy. The difference between them, the PV work term, is usually small for reactions involving solids and liquids, but can be significant for reactions involving gases, where volume changes can be substantial. There is one more concept in this territory that I want to make sure is clear, because it comes up in virtually every thermodynamics problem and is the source of many homework errors. It is the concept of heat capacity. Heat capacity tells you how much heat you need to add to a system to raise its temperature by 1 degree. A system with a large heat capacity takes a lot of heat to warm up. A system with a small heat capacity warms up easily. Water has a famously high heat capacity, which is why oceans moderate coastal climates and why a pot of water takes longer to boil than you'd expect. Metals typically have lower heat capacities, which is why a metal bench in the sun feels scorching, while a wooden bench beside it feels merely warm. Both are at the same temperature, receiving the same sunlight, but the metal conducts heat much more efficiently into your skin. But here is the thing that trips people up. There are two kinds of heat capacity, and they are different, and using the wrong one in a calculation will give you the wrong answer. Heat capacity at constant volume, written as CV, tells you how much heat is needed to raise the temperature by 1 degree while keeping the volume constant. In this case, no PV work is done, so all the heat goes into internal energy. Delta U equals NCV delta T, where N is the number of moles. Heat capacity at constant pressure, written as CP, tells you how much heat is needed to raise the temperature by 1 degree while keeping the pressure constant. In this case, the gas can expand, so some of the heat goes into internal energy and some goes into PV work. Delta H equals N CP delta T. CP is always larger than CV, always, because at constant pressure, you have to supply extra heat to cover the work of expansion in addition to the internal energy increase. The difference, for an ideal gas, is exactly R, the universal gas constant. Cp minus Cv equals R. That's a neat, clean relationship that comes directly from the ideal gas law. And the ratio of Cp to Cv, which is written as gamma, turns out to be incredibly important for adiabatic processes. For a monoatomic ideal gas like helium or argon, gamma equals 5/3, about 1.67. For a diatomic gas like nitrogen or oxygen, gamma equals 7/5, or 1.4. This ratio determines how steeply an adiabatic curve falls on a PV diagram compared to an isothermal curve. It determines how much a gas heats up when compressed adiabatically. It determines the speed of sound in a gas. It is one of those numbers that shows up everywhere once you start looking. The deeper reason Cp differs from Cv connects to something called degrees of freedom, which is the number of independent ways a molecule can store energy. A monoatomic gas can only move in 3 directions, x, y, and z. So it has 3 degrees of freedom, and each one contributes half kT of energy per molecule, where K is Boltzmann's constant and T is the temperature. A diatomic gas can translate in 3 directions and also rotate around 2 axes perpendicular to the bond, so it has 5 degrees of freedom. At very high temperatures, vibrational modes also become active, adding more degrees of freedom. The more degrees of freedom a molecule has, the more energy it can absorb for a given temperature increase, because the energy is being spread across more modes of storage. So molecules with more degrees of freedom have higher heat capacities. This is called the equipartition theorem, and it is a direct consequence of statistical mechanics, of Boltzmann's framework. The energy distributes itself equally among all available degrees of freedom, and the more places there are to put it, the more you need to put in to raise the temperature by 1 degree. All of this, every formula, every concept, every sign convention, rests on the first prohibition. Energy is conserved. You can track it. You can account for it. You can predict where it goes and how much ends up where. The first law is the accountant of the universe, meticulous, precise, and absolutely incorruptible. But accounting, as we said, only tells you the balance. It doesn't tell you which way the money flows. For that, you need the second prohibition. And for the practical question that every chemist and every engineer needs answered, will this reaction happen spontaneously, or won't it? You need something that combines both prohibitions into a single, elegant criterion. That criterion has a name. It is called Gibbs free energy, and it is, in many ways, the most useful concept in all of thermodynamics. We will return to Gibbs later. But before we move on to the second prohibition, there is one more thing the first law needs to answer for. Because throughout history, people have tried to cheat it. They have designed machines that they believed could create energy from nothing, or at least run forever without fuel. And every single one of them failed. The story of why is short, but it illuminates the first prohibition from a direction we haven't looked at yet. No tour of the 4 prohibitions would be complete without talking about the people who tried to break them. Because the history of thermodynamics is shadowed by a parallel history, a long, colourful, occasionally tragic parade of inventors who claim to have built machines that violated the first or second law. Perpetual motion machines. And their stories, besides being fascinating in themselves, illuminate the prohibitions from the other side, showing you what the universe looks like to someone who doesn't believe the rules apply. A perpetual motion machine of the first kind would violate the first prohibition. It would create energy from nothing. It would run forever without any fuel, any input, any source of energy whatsoever. Think of a wheel that turns by itself, driving a generator producing electricity, forever. No fuel, no batteries, no power cord, just endless, free energy. Nobody has ever built one. Nobody ever will. But people have tried, and some of the attempts have been remarkably clever. One of the most famous is the overbalanced wheel, a wheel with weights attached to hinged arms around its rim. The idea is that on one side of the wheel, the arms are extended outward, and on the other side, they fold inward. The extended arms, being further from the center, exert more torque, so the wheel should rotate continuously in one direction. Drawings of such devices go back to the 13th century, and people were still trying to build them in the 20th. The problem is that while the extended arms do exert more torque, there are fewer of them on the extended side at any given moment, because the geometry of folding and unfolding means the arms spend more time in the folded position than the extended one. The torques balance exactly. The wheel doesn't turn. The first prohibition holds. A perpetual motion machine of the second kind would obey the first prohibition, but violate the second. It wouldn't create energy from nothing. Instead, it would convert thermal energy from its surroundings entirely into work, without any cold reservoir, without any waste heat, without any increase in entropy. Imagine a ship that sailed the ocean by extracting heat from the seawater, cooling the ocean by a fraction of a degree, and converting that energy into motion. The energy is conserved. The ocean is enormous. There is an essentially unlimited supply of thermal energy. What could possibly stop it? The second prohibition stops it. Kelvin's formulation of the second law says it explicitly. You cannot extract heat from a single reservoir and convert it entirely into work with no other change. There must be a cold reservoir. There must be waste heat. There must be an entropy price. The ship that cools the ocean and converts the extracted heat entirely into motion cannot exist. The patent offices of the world have received thousands upon thousands of perpetual motion claims. The United States Patent Office stopped accepting them without a working model sometime in the 20th century, having grown weary of the parade. The British Patent Office has a similar policy. But inventors keep trying, often repackaging the old ideas in new language, calling them zero-point energy devices or over-unity generators or quantum vacuum engines. The names change. The physics doesn't. And here is what is most revealing about the perpetual motion seekers. Almost all of them are sincere. They genuinely believe they have found a loophole, a way around the prohibitions. They are not, for the most part, con artists, though some are. Most are enthusiastic amateurs who have grasped part of the physics but not all of it, who see an apparent imbalance in their machine and don't realize that they've left something out of their analysis, some subtle source of friction, some hidden energy drain, some accounting error in their entropy bookkeeping. And that is perhaps the deepest testament to the power of the prohibitions. They are not obvious. They are not intuitive. They go against our instincts in many ways. We feel like we should be able to get something for nothing, or at least break even. The universe says no. And the universe is very, very good at enforcing its rules. So the first prohibition holds. Energy cannot be created. Energy cannot be destroyed. The books always balance. You cannot win. But the first prohibition, as we saw, has a blind spot. It tells you the total stays the same, but it doesn't tell you which direction things flow. It doesn't explain why heat goes from hot to cold and never the other way. It doesn't explain why time moves forward and never backward. For that, we need the second prohibition. And the person who first glimpsed it was a young French military engineer's son who wanted to restore his country's glory. His name was Sadi Carnot, and his story begins with a letter to Napoleon. Sadi Carnot was born in 1796, right in the thick of revolutionary France. His father, Lazare Carnot, was one of the most powerful men in the country, a mathematician, military strategist, and political figure sometimes called the organizer of victory, for his role in directing the French revolutionary armies. So young Sadi grew up in a household where intellectual rigor and strategic thinking was simply the air you breathed. In 1813, France was being invaded by the armies of Austria, Prussia, and Russia. Napoleon's empire was crumbling. Sadi was 17 years old, a student at the École Polytechnique, and on December 29th, he wrote a letter to Napoleon requesting permission to join the fight. Napoleon, preoccupied with the desperate battles that would eventually cost him everything, never replied. But Carnot got his wish a few months later when Paris itself was attacked. The students of the École Polytechnique were sent to defend a chateau just east of the city. They were teenagers with weapons thrown against professional armies. They were no match. Paris fell after only a day of fighting, and Carnot was devastated. His world, the Napoleonic world of French power and prestige, collapsed around him. 7 years later, in 1820, the political dust had settled somewhat, and Sadi went to visit his father, who had fled to Prussia after Napoleon's downfall. And it was during this visit that something shifted. Lazare Carnot was not only a general, he was also a physicist who had written about how energy is most efficiently transferred in mechanical systems. Father and son talked at length about the great technological breakthrough of their age, the steam engine. And what they talked about worried them. British steam engines were better than French ones, significantly better. And in the early 19th century, when steam was driving factories, ships and railways, having better steam engines meant having a stronger economy and a more powerful military. France was falling behind. Carnot, the son of a man who had organized military victory, looked at this problem the way a strategist would. He wanted to understand, not just practically but theoretically, fundamentally, what governed the efficiency of a heat engine. Not any particular engine, but any engine that could ever be built. So he spent the next 3 years thinking about heat, about work, about the conversion of one into the other. And in 1824, when he was just 28 years old, he published a slim book called Reflections on the Motive Power of Fire. This book, this unassuming little volume, is one of the most remarkable documents in the history of science, because in it, Carnot asked a question that nobody had asked before, and the answer he found contained in embryonic form the second prohibition. His question was deceptively simple. Is there a limit to how efficient a heat engine can be? Is there some theoretical maximum, some ceiling that no amount of clever engineering can ever break through? Or could you, in principle, keep improving forever? To answer his question, Carnot did something brilliant. He abstracted away from every messy detail of every real engine. He forgot about the pistons, the boilers, the condensers, the particular fuel. the metal of the cylinders, the lubrication of the bearings. He imagined instead an ideal engine, a perfect engine, one with absolutely no friction, no heat leaking where it shouldn't, no wasted motion of any kind. And he asked, even for this perfect engine, even when every possible source of loss has been eliminated, is there still a maximum efficiency? Can you ever convert all the heat into work? Let me walk you through how Carnot's ideal engine works, because it is genuinely beautiful, and once you see it, you'll understand why the second prohibition exists. Take two very large metal bars. One is hot, the other is cold. Think of them as so massive that adding or removing a bit of heat doesn't change their temperatures at all. They are reservoirs, effectively infinite stores of thermal energy at fixed temperatures. The engine consists of a chamber filled with gas, with a piston inside connected to a flywheel. The engine runs in a cycle with 4 steps. Step 1. Place the chamber in contact with the hot bar. The gas absorbs heat from the hot bar and expands. Because heat is flowing in to replace what the gas spends on expansion, the temperature stays constant. The gas pushes the piston up, turning the flywheel. This step is called isothermal expansion. Step 2. Remove the hot bar. The gas continues to expand, but now no heat is entering. The gas is spending its own internal energy to do the work of pushing the piston, so its temperature drops. It cools down. This continues until the gas reaches the temperature of the cold bar. This step is called adiabatic expansion because no heat is exchanged. Step 3. Place the chamber in contact with the cold bar. Now the flywheel pushes the piston back down, compressing the gas. As the gas is compressed, it would naturally heat up. But because it is in contact with the cold bar, the heat generated by compression flows out into the cold bar. The temperature stays constant. This is isothermal compression. Step 4. Remove the cold bar. The flywheel continues compressing the gas. Now there is no cold bar to absorb the heat of compression, so the gas heats up. It heats up until it reaches the temperature of the hot bar. This is adiabatic compression. And now we are back where we started. The gas is at the temperature of the hot bar. The piston is in its starting position, and the cycle can begin again. Through this cycle, heat from the hot bar has been partially converted into the energy of the flywheel. The flywheel gained energy. That energy came from the difference between the heat absorbed from the hot bar and the heat dumped into the cold bar. Each cycle, the flywheel gets a bit more energy. Now, here is what is remarkable about Carnot's ideal engine. It is completely reversible. If you ran the entire cycle backward, first expanding the gas while in contact with the cold bar to draw heat out of it, then compressing while in contact with the hot bar to push heat back in, you could return every single joule of energy to exactly where it started. The flywheel would give back its energy, the hot bar would regain its heat, the cold bar would lose what it gained. Nothing would be different. You could run the engine forward for 1,000 cycles, and then backward for 1,000 cycles, and at the end, the universe would be in exactly the same state as when you started. The process is perfectly reversible, perfectly symmetric in time. And you might expect that a perfectly reversible engine, one that loses nothing to friction, nothing to leaks, nothing to any form of waste, would be 100% efficient. That it would convert all the heat from the hot bar into work in the flywheel. But it does not. And this is where the second prohibition lives. Each cycle, the engine must dump some heat into the cold bar. It has to. There is no way around it. The compression step on the cold side requires it. You cannot return the piston to its starting position without compressing the gas, and you cannot compress the gas without generating heat, and that heat has to go somewhere. It goes into the cold bar. So the energy gained by the flywheel is always less than the heat taken from the hot bar. Some of the heat passes through the engine without doing any work at all. Carnot showed that the efficiency of his ideal engine depends only on the temperatures of the hot and cold bars. If we use the absolute temperature scale, the Kelvin scale, the efficiency is 1 minus the ratio of the cold temperature to the hot temperature. That's it. Efficiency equals 1 minus T cold divided by T hot. The only way to reach 100% efficiency would be to have the cold bar at absolute 0 Kelvin, or the hot bar at infinite temperature. Both are impossible. Let that sink in for a moment. Even in a perfect world with a perfect engine, with no friction, no leaks, no losses of any kind, you still cannot convert all heat into work. The universe prohibits it. There is a fundamental, inescapable ceiling on efficiency, and that ceiling is set not by engineering, not by materials, not by cleverness, but by the temperatures involved. Period. In Carnot's time, the best high-pressure steam engines could reach temperatures of about 160 degrees Celsius, which is about 433 Kelvin. With a cold side at roughly room temperature, about 300 Kelvin, the theoretical maximum efficiency was around 32%. The actual efficiency of real engines at the time was about 3%. The gap between the theoretical maximum and reality was enormous, which meant there was room for improvement, but Carnot had drawn a line that could never be crossed. The gap between 3% and 32% is the story of irreversibility. Carnot's ideal engine is reversible. Real engines are not, and the difference matters enormously. In a real engine, friction is everywhere. The piston scrapes against the cylinder walls. The bearings resist the turning of the crankshaft. Every moving part wastes a fraction of the energy as heat that spreads into the metal, into the oil, into the environment. That heat is gone. You cannot recover it. It has spread out, become diffuse, become part of the general background warmth of the surroundings. Getting it back would be like trying to unstir cream from coffee. In a real engine, heat doesn't transfer at constant temperatures. The gas doesn't stay perfectly at the temperature of the hot bar during expansion. There's always a temperature difference needed to drive the heat transfer, and that difference means the process isn't truly isothermal, which means it isn't truly reversible. In a real engine, the gas doesn't expand and compress in perfect, infinitely slow steps. The processes happen at finite speed, which means the gas is never quite in equilibrium, which means there are always small eddies, turbulences, pressure gradients inside the gas that waste energy. All of these real-world imperfections push the actual efficiency below the Carnot limit. They create losses, and those losses are irreversible. The energy isn't destroyed, the first law still holds, but it becomes less useful. It spreads out, it becomes diffuse, it becomes unavailable for doing work. The total amount of energy in the universe stays the same, but the fraction of that energy that can actually be used to do something interesting decreases with every irreversible process. And this is where a quiet, methodical German physicist enters the story. The man who would give this spreading out a name, a formula, and a place in the architecture of physics that it has occupied ever since. Rudolf Clausius. We met him briefly in the chapter on the first law, but his deepest contribution was still ahead. If Carnot discovered the territory, Clausius drew the map. Clausius spent years thinking about what made Carnot's ideal engine special and what made real engines fall short. He kept coming back to a question that seems simple but turns out to be profound. When heat flows from a hot object to a cold one, something happens that cannot be undone. The energy is still there, but something has changed. Something has been lost, not energy but something else. Some quality that the energy had before, some capacity to do work, some potential that existed when the energy was concentrated in the hot object, and that no longer exists now that the energy is spread between the hot object and the cold one. What is that something? What exactly is lost when energy spreads out? Clausius worked on this from the early 1850s through the mid-1860s, refining his ideas year by year, paper by paper. In those early papers, he talked about what he called the equivalence value of transformations, which is a clunky phrase that he knew wasn't quite right. He was groping towards something, reaching for a concept that didn't yet have a name. In 1865, he found it. He introduced a new quantity, a measure of how spread out the energy in a system is, a measure of how much of the energy has become unavailable for doing work. He called it entropy, deliberately choosing a word from the Greek trope, meaning transformation or turning, to echo the word energy. He wanted the two concepts to feel like siblings, because in a deep sense, they are. Energy tells you how much, entropy tells you which way. And he summarized the two laws of thermodynamics in what might be the most elegant pair of sentences in all of physics. The energy of the universe is constant. The entropy of the universe tends toward a maximum. Read those two sentences again slowly. The first says nothing is created, nothing is destroyed. The second says everything spreads out. Together, they paint a picture of a universe where the total energy never changes, but that energy is constantly becoming less useful, constantly dispersing, constantly moving from concentrated, ordered, potent forms into dilute, scattered, impotent ones. Your hot coffee and the cool room contain the same total energy before and after the coffee cools down. But before, there was a temperature difference, a gradient, a potential. That potential could have been used. You could have run a tiny heat engine between the hot coffee and the cool room and extracted a tiny amount of work. After, when everything is at the same temperature, that potential is gone. The energy is still there, but the entropy has increased and the capacity to do work has decreased. Entropy is not disorder exactly, despite what every popular science book will tell you. The word disorder is not wrong, but it is misleading because it suggests messiness, chaos, things out of place, and that is only part of the picture. Entropy is better understood as the spreading out of energy. When energy is concentrated, entropy is low. When energy is dispersed, entropy is high. And the second law says that in any real process, the total entropy of the universe either stays the same, if the process is perfectly reversible, which never actually happens, or increases. It never decreases. Never. The arrow points one way. But why? Why does entropy increase? Clausius described the tendency and gave it a name and a formula, but he didn't explain why it happens. The explanation came from a man whose genius was matched only by the suffering his ideas brought him. Ludwig Boltzmann was born in Vienna in 1844. He was a theoretical physicist with a big personality, a man who loved the outdoors, loved music, loved vigorous debate, and loved ideas with a passion that bordered on the physical. His great contribution was to connect the macroscopic world of thermodynamics, the world of temperatures and pressures and heat flows, to the microscopic world of atoms and molecules. In Boltzmann's time, many scientists didn't believe atoms were real. This might seem strange to us now, but in the late 19th century, the existence of atoms was genuinely controversial. Influential thinkers like Ernst Mach and Wilhelm Ostwald argued that atoms were a useful fiction, a mathematical tool, not real physical entities. You couldn't see them, you couldn't weigh them individually. Why believe in them? Boltzmann believed in them with every fiber of his being, and he showed that if you took atoms seriously, if you treated a gas as a vast collection of tiny particles bouncing around randomly, colliding with each other and with the walls of their container, then the macroscopic properties of the gas, its temperature, its pressure, its entropy, all emerged naturally from the statistical behavior of those particles. Temperature was the average kinetic energy of the particles. Pressure was the force of particles hitting the walls. And entropy, Boltzmann showed, was related to the number of microscopic configurations that correspond to a given macroscopic state. Let me explain what that means. because it is one of the deepest insights anyone has ever had about the physical world. Imagine you have two metal bars, one hot and one cold. Hot means the atoms in that bar are vibrating vigorously with lots of energy. Cold means the atoms are vibrating gently with less energy. Now bring the bars into contact and let them share energy. The energy packets can hop randomly from atom to atom, spreading across both bars. Here is the key question. How many different ways can the energy be arranged? If almost all the energy is concentrated in the hot bar, there are relatively few ways to arrange it. If the energy is spread evenly between both bars, there are enormously more ways. The evenly spread state isn't special physically, it is special statistically. There are just far, far more microscopic arrangements that correspond to energy spread evenly than to energy concentrated on one side. Boltzmann's formula captures this. He wrote S equals K log W, where S is the entropy, K is a constant that we now call Boltzmann's constant, and W is the number of microscopic configurations, the number of different ways the atoms and their energies could be arranged while still giving the same macroscopic appearance. The more ways, the higher the entropy. And the reason entropy increases is simply this. A system that is free to explore its possible configurations will, over time, tend toward the configurations that are most numerous. Not because there is a force pushing it there, not because there is a law commanding it, simply because there are overwhelmingly more of those configurations to fall into. It is the same reason that if you shuffle a deck of cards, you are overwhelmingly likely to end up with a random-looking arrangement rather than a perfectly ordered one. Not because random arrangements are somehow preferred by the cards. There are just so many more of them. Think of it like a Rubik's Cube. There is exactly one configuration where the cube is perfectly solved. There are a few configurations where it is nearly solved. And there are roughly 43 quintillion configurations where it is a scrambled mess. If you close your eyes and start making random turns, you will move from the solved state to a messier state, and then to an even messier one. Not because there is a force pushing the cube toward disorder, but because at every step there are overwhelmingly more disordered states to land in than ordered ones. Without deliberate, intelligent effort, the cube will never return to its solved state. The probability is so small that it is effectively zero. And that is why your coffee cools down but never heats back up. The atoms in the coffee and the air are bouncing around randomly, sharing energy. And there are staggeringly more configurations where the energy is spread evenly between coffee and air than configurations where the energy is concentrated in the coffee. The coffee will eventually reach the temperature of the room, and once it does, it will stay there, because returning to a state with all the energy concentrated in the coffee would require all those randomly bouncing atoms to conspire, to coordinate, to all push their energy in the same direction at the same time. The probability of that happening is not zero. Boltzmann was very clear about this. It is not impossible for heat to flow from cold to hot spontaneously. It is just so incredibly, absurdly, overwhelmingly improbable that it never happens in practice. With the number of atoms in a real cup of coffee, roughly 10 to the 25th power, the probability of a spontaneous reversal is so small that you would have to wait longer than the age of the universe, far longer, inconceivably longer, for it to happen even once. So the second prohibition is not really a prohibition in the absolute sense. It is a statistical certainty, so certain that it might as well be absolute, so certain that in practice it is indistinguishable from a hard law. The universe doesn't forbid entropy from decreasing. It just makes the alternative so overwhelmingly likely that the question is moot. This is Boltzmann's great insight. He connected the macroscopic arrow of time, the fact that things always evolve in one direction, toward greater entropy, toward more spread-out energy, to the microscopic world of atoms and probability. He showed that the second law of thermodynamics is not a mysterious cosmic decree. It is a consequence of counting, of mathematics, of the simple fact that some arrangements are more numerous than others. But Boltzmann paid a terrible price for his vision. The scientific establishment of his time was deeply divided over the existence of atoms, and Boltzmann found himself on the wrong side of the dominant faction. Ernst Mach, a hugely influential philosopher and physicist, rejected the atomic hypothesis entirely. He believed that science should deal only with observable quantities, with things you could measure directly, and atoms were not observable. Mach considered Boltzmann's statistical mechanics to be built on a fantasy, and he said so publicly, repeatedly, and caustically. Ostwald, another prominent scientist, went further. He argued that the concept of energy was sufficient to explain everything in physics, and that atoms were not only unnecessary but actively misleading. He called his approach energetics, and positioned it as a superior alternative to Boltzmann's atomistic view. Boltzmann fought back. He was passionate in defense of his ideas, sometimes too passionate. The debates were public, they were heated, and they were personal. And as the years went on, Boltzmann found himself increasingly isolated. He suffered from depression, possibly bipolar disorder, though diagnosis across more than a century is always uncertain. The constant attacks on his life's work took a toll. He felt unheard. He felt rejected. In September 1906, while on vacation with his family in Duino, near Trieste, Ludwig Boltzmann took his own life. He was 62 years old. The bitter irony is that within a few years of his death, his vindication came. In 1905, just a year before Boltzmann died, Albert Einstein published his paper on Brownian motion, showing that the random jiggling of tiny particles suspended in water was exactly what you would expect if the water were made of atoms constantly bombarding those particles from all sides. It was, in effect, direct evidence for the existence of atoms. Jean Perrin's subsequent experiments confirmed Einstein's predictions in beautiful detail, and by about 1910, the atomic hypothesis was accepted by virtually everyone. Boltzmann didn't live to see it. He died thinking his life's work had failed. His formula, S equals K log W, is engraved on his tombstone in Vienna's Central Cemetery. It is one of the most important equations in all of physics, and it is a monument not only to a great idea, but to a man who was destroyed by the gap between when he saw the truth and when the world was ready to accept it. Let me pull back from the history and the tragedy and state the second prohibition clearly, because it shows up in several different forms, and the relationship between those forms is important. Clausius stated it this way: heat cannot, of itself, pass from a colder body to a warmer one. Of itself is the key phrase. It means without some other change happening, without work being done, without compensation somewhere else. Heat flows from hot to cold spontaneously. Getting it to flow from cold to hot requires effort, and that effort always generates more entropy than it eliminates. Lord Kelvin stated it differently. It is impossible to construct a device that, operating in a cycle, produces no effect other than the extraction of heat from a single reservoir and the performance of an equivalent amount of work. In other words, you cannot build an engine that takes heat from, say, the ocean, which contains an enormous amount of thermal energy, and converts all of it into useful work with nothing left over. There must always be waste heat dumped into a cooler reservoir. Always. Not because of engineering limitations, but because of the second prohibition. These two statements, Clausius's and Kelvin's, sound like they are saying different things, but they are logically equivalent. If one is violated, the other must be too. They are two windows looking at the same room, and Boltzmann gave the statistical version. Entropy increases because high entropy states are overwhelmingly more probable than low entropy states. The system doesn't know about entropy. The atoms don't know about the second law. They just bounce around randomly. And the random bouncing purely by the mathematics of large numbers, drives the system toward the most probable arrangement, which is the one with the highest entropy, which is the one where the energy is most spread out. There is a beautiful thought experiment that illustrates the second prohibition in action, and it comes from one of the most famous thought experiments in all of physics. James Clerk Maxwell, the same Maxwell who unified electricity and magnetism, imagined a tiny being, a demon, sitting at a door between two chambers of gas. The demon can see individual molecules, and every time a fast molecule comes from the left, the demon opens the door and lets it through to the right. Every time a slow molecule comes from the right, the demon opens the door and lets it through to the left. Over time, the right side gets hotter, the left side gets cooler, and the demon has apparently violated the second law without doing any work. For decades, this was a genuine puzzle. It was eventually resolved by a series of insights, the most important being Leo Szilard's in 1929 and Rolf Landauer's in 1961. They showed that the demon must process information. It must observe, record, and act on the positions and speeds of molecules, and that information processing has a thermodynamic cost. Erasing information, which the demon must do to keep operating, generates entropy, and that entropy is at least as much as the entropy the demon eliminates by sorting molecules. The books still balance. The second prohibition still holds. Even information is subject to the tax. Even computation has a thermodynamic cost. The second prohibition reaches deeper than anyone initially suspected. There is a question that comes up almost immediately when people hear the second prohibition stated as, "Heat cannot flow from cold to hot." And the question is, what about my refrigerator? My refrigerator makes cold things colder and the warm kitchen warmer. Heat is flowing from cold to hot, every day, in kitchens around the world. And the answer is yes, heat is flowing from cold to hot inside your refrigerator. But it is not flowing of itself. There is a compressor, and the compressor is doing work. And that work is being paid for by electricity, which came from a power plant, which burned fuel, which generated entropy. The decrease in entropy inside your refrigerator, the removal of heat from the cold interior, is more than compensated by the increase in entropy at the power plant and in all the wires and motors and components in between. Let me walk you through how this actually works, because it is a beautiful illustration of the second prohibition being obeyed even while it seems to be defied. Inside your refrigerator, there is a closed loop of refrigerant, a special fluid that evaporates and condenses at useful temperatures. The cycle goes like this. The refrigerant, in liquid form, passes through an expansion valve into the evaporator coils inside the fridge. As it expands, it evaporates, turning from liquid to gas. Evaporation absorbs heat, just like sweat evaporating from your skin cools you down. So the refrigerant absorbs heat from the food inside the fridge, making the food colder. The refrigerant, now a warm gas, flows to the compressor, which compresses it. Compression raises its temperature significantly, making it hotter than the kitchen air. The hot, compressed gas then flows through the condenser coils on the back or bottom of the fridge, where it releases its heat into the kitchen. The refrigerant condenses back into a liquid, and the cycle repeats. At no point does heat flow from cold to hot on its own. The compressor does the work of compressing the gas, raising its temperature above that of the kitchen, so that heat can flow from the gas to the kitchen naturally, from hot to cold. The compressor is the intermediary. The compressor is the reason the second prohibition is not violated. And the electricity powering the compressor came from somewhere. At a power plant, concentrated chemical energy in coal or gas was burned, heating steam, spinning turbines, generating electricity, with enormous amounts of waste heat radiated into the environment at every step. The total entropy of the universe went up, the local decrease in entropy inside your refrigerator was purchased at the cost of a much larger increase in entropy elsewhere. This is the second prohibition in action. You can decrease entropy locally. You can create pockets of order, cold spaces, organized structures, living things. But only by increasing entropy somewhere else by an even greater amount. The total always goes up. Now, you might look at all of this and feel a certain despair. If everything is running down, if entropy always increases, if the useful energy in the universe is constantly being degraded into useless heat, then what's the point? Isn't the universe just winding down like a clock, destined for a final, featureless, lukewarm equilibrium? The answer to that question involves the third prohibition, a prohibition so extreme that it guarantees a certain kind of immortality to the process of winding down itself. Because the third prohibition says you can't even get to the bottom. You can never reach absolute zero. You can never get all the way to the end. The game goes on forever, getting slower and quieter, but never, ever stopping completely. But before we go there, let me leave you with one more thought about the second prohibition. Because there is a detail that is easy to miss, and it changes everything. The second law creates the arrow of time. Without the second prohibition, there would be no difference between past and future. The fundamental laws of physics, the equations of motion for particles, electromagnetism, even quantum mechanics, all work exactly the same forward and backward in time. If you filmed a collision between two billiard balls and ran the film in reverse, both versions would look perfectly physical. But if you filmed a cup of coffee cooling down and ran the film in reverse, showing the coffee spontaneously heating up while the room cools, everyone would immediately know something was wrong. That doesn't happen. And the reason it doesn't happen is the second prohibition. Entropy increases toward the future. That is what defines the future. The direction of increasing entropy is the direction of time. Without the second prohibition, the universe would have no history, no before and after, no cause and effect, no memory, no life. The second prohibition doesn't just tell you what can't happen. It creates the framework within which anything can happen at all. And with that in mind, let's talk about the final wall, the coldest prohibition, the one that tells the universe it can never fully come to rest. I want to return to a concept we touched on earlier, because it is one of the most subtle and most important ideas in all of thermodynamics, and it is also one of the most confusing. The concept of reversibility. A reversible process is one that can be undone completely, leaving both the system and the surroundings in exactly the states they were in before the process happened. No trace, no residue, no memory that anything happened at all. Perfect symmetry between forward and backward. In practice, no real process is reversible. Every real process involves some friction, some heat dissipation, some departure from equilibrium. But the idea of a reversible process is enormously useful as a theoretical benchmark, the thermodynamic equivalent of a frictionless surface in mechanics. You know it doesn't exist, but imagining it helps you understand the limits of what is possible. The key characteristic of a reversible process is that the system is always infinitesimally close to equilibrium. Every step of the process is taken so slowly, so gently, that the system has time to fully adjust before the next step begins. If you are compressing a gas reversibly, you increase the external pressure by an infinitesimally tiny amount, just barely more than the gas pressure, and you wait for the gas to adjust. Then you increase the pressure by another infinitesimal amount, and wait again, and so on. The process takes, in principle, an infinite amount of time, because each step is infinitely small, and you have to take an infinite number of them. This is obviously impractical. Nobody has infinite time. But the concept matters because reversible processes represent the absolute best case. They extract the maximum possible work from an expansion. They require the minimum possible work for a compression. Any real process, any irreversible process, will extract less work or require more work than the reversible version of the same process. Think about it this way. If you let a gas expand suddenly, explosively, against a much lower external pressure, the gas rushes outward, creating turbulence, eddies, internal friction. Energy is wasted in all that chaotic motion. The gas does less useful work than it would have if it had expanded slowly, gently, reversibly, always pushing against an external pressure that was just barely less than its own. The difference between reversible and irreversible work is directly related to entropy. In a reversible process, the total entropy of the universe doesn't change. The entropy gained by one part is exactly offset by the entropy lost by another. In an irreversible process, entropy is created, generated out of the irreversibility itself. Friction generates entropy. Turbulence generates entropy. Rapid expansion against a vacuum generates entropy. The faster you go, the further from equilibrium you are, the more entropy you create, and the less work you get out. This is why Carnot's ideal engine represents the maximum possible efficiency. Carnot's cycle is reversible. Every step is conducted infinitely slowly, always at equilibrium. No friction, no turbulence, no temperature gradients within the gas. The result is the maximum conversion of heat into work, set by the Carnot efficiency formula. 1 minus T cold over T hot. Any real engine, with its inevitable irreversibilities, will fall short of this ideal. And this is also why the second prohibition is sometimes stated in terms of reversibility. In a reversible process, the entropy of the universe stays constant. In any irreversible process, the entropy of the universe increases. Since all real processes are irreversible, the entropy of the universe is always increasing. The reversible process is the boundary between what is thermodynamically possible and what is thermodynamically forbidden. It is the line on the map between the territory you can reach and the territory you cannot. There is a practical formula that comes out of this analysis, and it is the formula for work done in a reversible isothermal expansion of an ideal gas. If you expand a gas reversibly and isothermally from volume V1 to volume V2, the work done by the gas is W equals nRT times the natural logarithm of V2 over V1. If V2 is larger than V1, the gas has expanded, and the work is positive, meaning the gas did work on its surroundings. This formula comes from integrating the pressure over the change in volume, using the ideal gas law to express pressure as nRT over V. Using Boyle's law, which says that at constant temperature, P1V1 equals P2V2, you can also write this as W equals nRT times the natural logarithm of P1 over P2. Same formula, different variables. These two forms show up in thermodynamics problems constantly, and being comfortable with both is essential for working through the quantitative side of the subject. For an irreversible expansion against a constant external pressure, the formula is different and gives less work. W equals negative P external times delta V, where P external is the constant external pressure and delta V is the change in volume. Since the external pressure in an irreversible expansion is less than the gas pressure, the gas does less work than in the reversible case. The difference is wasted as entropy generated within the gas. If you plot both processes on a PV diagram, the reversible isothermal expansion follows a smooth hyperbolic curve, and the work done is the area under that curve. The irreversible expansion against a constant external pressure follows a horizontal line at P external, and the work done is the area of a rectangle, which is smaller than the area under the curve. The difference between the two areas is the work that was lost to irreversibility. Seeing this on a graph makes it viscerally clear why reversibility matters. The reversible process squeezes the maximum work out of the expansion. The irreversible process leaves work on the table. And the second prohibition tells you that you can never do better than reversible. You can approach it, get close, optimize your engineering, but you can never exceed it. The reversible limit is the wall. There is a temperature at which all thermal motion stops, where atoms and molecules cease their restless vibrations, where the kinetic energy that manifests as heat drops to the absolute minimum allowed by the laws of physics. That temperature is 0 Kelvin, minus 273.15 degrees Celsius. Absolute zero. And you can never get there. That is the third prohibition. You can get close. You can get astonishingly, breathtakingly close. Modern laboratories have cooled matter to within billionths of a degree of absolute zero. But reaching it exactly, touching the bottom, arriving at the point where entropy would itself reach zero, or its minimum possible value, that is forbidden. The closer you get, the harder it becomes. And the last infinitesimal step requires infinite effort. The bottom is a horizon that recedes as you approach it. The story of how this prohibition was discovered is quieter than the stories of the first and second laws. There is no tragic figure consumed by rejection. There is no young military engineer dying of cholera with his papers burned. The third law emerged gradually, through careful, meticulous work, driven largely by one man whose precision was legendary, and whose personality was, by most accounts, formidable. Walter Nernst was born in 1864 in Briesen, in what was then the Prussian province of West Prussia. He was a physical chemist, a breed of scientist that sat at the intersection of physics and chemistry, and that was gaining influence rapidly in the late 19th century. By the early 1900s, Nernst was one of the most prominent scientists in Germany, a professor in Berlin, well-connected, ambitious, and relentlessly productive. Nernst's interest in the third law grew out of a very practical problem. Chemists wanted to predict whether a chemical reaction would happen spontaneously. They had tools for this, involving quantities called free energy and entropy. But those tools required knowing the absolute values of entropy for various substances. And in the early 1900s, there was no way to determine absolute entropies. You could measure changes in entropy, sure, but not the starting point, not the zero. In 1906, Nernst proposed what he called his heat theorem. It stated that as the temperature of a system approaches absolute zero, the entropy change associated with any process also approaches zero. In simpler terms, at absolute zero, all pure, perfectly crystalline substances have the same entropy, and that entropy is zero. This is sometimes stated as the third law of thermodynamics. Now, why does this matter? Because it gives you a reference point. If you know that entropy is zero at absolute zero for a perfect crystal, then you can calculate the absolute entropy at any higher temperature by measuring how much entropy is added as you warm the substance up from zero. You finally have a baseline, a starting point for the entropy scale. But there is a much deeper implication hiding in the third law, and it took time for it to emerge fully. The deeper implication is about the impossibility of reaching absolute zero itself. Think about what it would mean to cool something to absolute zero. You would need to remove every last bit of thermal energy from every atom, every vibration, every degree of freedom. And to remove heat from something, you need somewhere colder to dump it, because heat flows from hot to cold. But if you are trying to reach absolute zero, there is nothing colder. You are trying to reach the very bottom. Where do you dump the last bit of heat? The answer is that each successive step of cooling removes less and less entropy, and the amount of work required for each step grows without bound. Cooling from 100 Kelvin to 50 Kelvin is hard but manageable. Cooling from 10 Kelvin to 5 Kelvin is much harder. Cooling from 1 Kelvin to half a Kelvin is harder still. Cooling from 1 millikelvin to half a millikelvin requires extraordinary effort. And cooling from any finite temperature to exactly zero would require an infinite number of steps, each extracting a smaller and smaller amount of entropy. You can approach the limit. You can get arbitrarily close, but you can never arrive. This is sometimes stated as the unattainability principle, and it is equivalent to Nernst's entropy formulation. Both say the same thing in different words. Absolute zero is a limit that can be approached, but never reached. Now, there is a subtlety here that is worth mentioning, because it connects the third law to something much deeper. When Nernst said that the entropy of a perfect crystal at absolute zero is zero, the word perfect is doing important work. A perfect crystal means every atom is in its proper place, in a perfectly ordered lattice, with no defects, no impurities, no randomness of any kind. In such a crystal, there is exactly one microscopic configuration, one way to arrange the atoms. Boltzmann's formula says S equals K log W, and if W equals 1, log 1 is 0, so S equals 0. There is no uncertainty about where the atoms are. There is no randomness. There is no disorder. Entropy is 0. But real crystals are never perfect. They have defects, vacancies, misplaced atoms, and certain substances like glass are not even crystalline. They are amorphous, with atoms frozen in a disordered arrangement. Such substances retain what is called residual entropy, even at absolute zero. They don't reach S equals 0 because they are not perfectly ordered. And even in a perfect crystal, there is a quantum mechanical flaw. The Heisenberg uncertainty principle says you cannot simultaneously know the exact position and momentum of a particle with perfect precision. At absolute zero, particles don't actually stop moving completely. They have what is called zero-point energy, a minimum energy that cannot be removed, a consequence of the fundamental quantum nature of reality. Even at the very bottom, there is a kind of irreducible jitter, a whisper of motion that can never be silenced. So the third prohibition is not just an engineering challenge, it is woven into the fabric of quantum mechanics. The universe has a flaw, and you cannot stand on it. You can hover just above it, closer and closer, but touching it requires violating something more fundamental than just thermodynamics. Let me bring this back to the framework of prohibitions. The first prohibition says you can never create or destroy energy. You are stuck with what you have. You cannot win. The second prohibition says that in every real process, some energy becomes unavailable. You cannot even break even. And the third prohibition says you can never reach the state where all useful energy has been extracted, where entropy is at its absolute minimum, where everything has stopped. You cannot leave the game. There is a famous way of summarizing all three prohibitions that has been attributed to various people, and it goes like this. You can't win, you can't break even, and you can't quit. That might sound bleak. It might sound like the universe has set up a game where the rules are stacked against you and there's no way out. But I want to suggest, very gently, that the opposite is true. These prohibitions are what make the game worth playing, because without them, there would be no game at all. And that is what the final chapter of our story tonight is about. Not what the four prohibitions prevent, but what they create. Before we return to the finale, I want to tell you about the practical pursuit of the third prohibition, because it is one of the most extraordinary chapters in experimental physics, and it illustrates the prohibition with breathtaking clarity. The quest to reach absolute zero began in earnest in the late 19th century, and has continued ever since, with each generation of scientists pushing the temperature lower and lower, using ever more ingenious techniques. The first great breakthrough came from the liquefaction of gases. If you compress a gas and then let it expand, it cools down. This is the principle behind your refrigerator. But ordinary refrigeration can only get you so far. To reach really low temperatures, you need to liquefy gases that are normally gases at room temperature, and then use their evaporation to cool things further.
In 1877, Louis-Paul Cailletet in France and Raoul Pictet in Switzerland independently liquefied oxygen for the first time, reaching temperatures around -183 degrees Celsius, roughly 90 Kelvin. This was a dramatic achievement, but it was just the beginning. The next target was nitrogen, which liquefies at 77 Kelvin. Then hydrogen, which was liquefied by James Dewar in 1898 at about 20 Kelvin. Each new liquid gas provided a colder bath, a colder starting point for the next stage of cooling. But the real prize was helium. Helium has the lowest boiling point of any substance, just 4.2 Kelvin, -269 degrees Celsius. Liquefying helium was the Mount Everest of cryogenics, and the man who conquered it was Heike Kamerlingh-Onnes, a Dutch physicist working at the University of Leiden.
On July 10, 1908, after years of careful preparation, Kamerlingh-Onnes succeeded in liquefying helium for the first time. He cooled it to 4.2 Kelvin, just a few degrees above absolute zero. And then, something remarkable happened. While studying the properties of metals at these extreme temperatures, Kamerlingh-Onnes discovered that mercury, when cooled below about 4 Kelvin, completely lost its electrical resistance. Current flowed through it without any loss, without any heating, without any friction at all. He had discovered superconductivity, a phenomenon that was completely unexpected and that would take decades to explain. The third prohibition was creating wonders at the very boundary it guarded. Since Kamerlingh-Onnes, scientists have pushed ever closer to absolute zero. By pumping on liquid helium, reducing the pressure above it, they could cool it below its normal boiling point, reaching temperatures of about 1 Kelvin. By using the rarer isotope helium-3, which becomes a superfluid at even lower temperatures, they reached millikelvins. Then came an entirely different technique, adiabatic demagnetization. You take a paramagnetic salt, apply a strong magnetic field, which lines up the magnetic moments of the atoms and reduces their entropy. Then you isolate the salt thermally and remove the magnetic field. The moments randomize again, increasing entropy, and the temperature drops because the entropy increase must come at the expense of thermal energy. Using this technique, scientists reached microkelvins, millionths of a degree above absolute zero. And then came laser cooling and evaporative cooling of atom clouds, techniques developed in the 1980s and 90s, which brought temperatures down to nanokelvins, billionths of a degree above absolute zero. In 1995, Eric Cornell and Carl Wieman at the University of Colorado created the first Bose-Einstein condensate, a state of matter predicted by Einstein and Bose in the 1920s, where atoms cooled to near absolute zero lose their individual identities and behave as a single quantum entity. The temperature was about 20 nanokelvins. As of the most recent records, laboratories have reached temperatures in the picokelvin range, trillionths of a degree above absolute zero. Each new record is harder to achieve than the last. Each increment closer to zero requires more effort, more ingenuity, more energy. The pattern is clear and relentless. You can always get a bit closer, but you can never arrive. The third prohibition holds. And notice something about the progression. Each new cooling technique works by removing entropy from the system, by ordering the atoms, by reducing the number of available states. And each technique runs into its own limits, its own irreducible entropy flaw, requiring the next technique to take over. Compression and expansion get you to a few Kelvin. Pumping gets you to fractions of a Kelvin. Demagnetization gets you to microkelvins. Laser cooling gets you to nanokelvins. Each step is harder, slower, more delicate than the last. The third prohibition isn't just an abstract statement, it is written in the sweat and frustration and brilliant ingenuity of every experimentalist who has ever chased absolute zero. They know, better than anyone, that the bottom is real and that it is unreachable. And they keep chasing it anyway, because the phenomena they discover along the way, superconductivity, superfluidity, Bose-Einstein condensation, quantum effects writ large. These phenomena are among the most extraordinary in all of physics. The third prohibition guards a boundary, and the boundary, like all boundaries in thermodynamics, is not a dead end.
It is a horizon, endlessly receding, endlessly revealing new wonders as you approach. Here is the question that might have been forming in your mind over the last hour or so. If entropy always increases, if energy always spreads out, if the useful fraction of the universe's energy is constantly shrinking, then how is there any structure left? How are there hot things next to cold things? How are there stars burning in the void? How are there crystals and snowflakes and mountains and rivers? How are there living things, spectacularly organized, improbably complex living things that grow, move, reproduce, think, and lie in the dark listening to stories about thermodynamics? If the second prohibition is always pushing toward uniformity, toward featurelessness, toward the dull, grey equilibrium of maximum entropy, then how does complexity exist at all? The answer comes in two parts. The first part is simple. The second is profound. The simple part is that the Earth is not a closed system.
If the Earth were sealed off from the rest of the universe, receiving no energy from outside and radiating none away, then yes, everything on Earth would eventually reach thermal equilibrium. All temperatures would equalize, all chemical reactions would stop, all gradients would vanish. Everything would be the same temperature, the same composition, the same featureless uniformity. Life would end, structure would dissolve, entropy would reach its maximum, and nothing interesting would ever happen again. But the Earth is not sealed off. We have the Sun, and here is where the story takes an unexpected turn, because what the Sun gives us is not what most people think. If you ask people what we get from the Sun, almost everyone will say energy, and they're not wrong, but they're not quite right either. Because the Earth radiates almost exactly as much energy back into space as it receives from the Sun. If it didn't, the planet would be getting hotter and hotter, which, concerns about climate change aside, is not what has been happening over geological timescales. For most of Earth's history, energy in has roughly equaled energy out. The books balance. So if we're not keeping the energy, what are we actually getting? The answer is low entropy. The Sun gives us energy in a concentrated, high-quality, low-entropy form as a relatively small number of very high-energy photons. These are photons of visible light, each one carrying a substantial amount of energy in a compact package. The Earth absorbs that concentrated energy and uses it, and in using it, degrades it, and then radiates it back into space as a much larger number of much lower energy photons, infrared radiation, thermal radiation, each one carrying only a fraction of the energy that the incoming photons carried. The number is striking. For every photon the Earth receives from the Sun, it radiates roughly 20 photons back into space. The total energy is the same, going in and going out. But the energy going out is spread across 20 times as many photons, each one individually less energetic. The entropy has increased. The energy has been spread out, dispersed, diluted. And everything that happens on Earth, everything, happens in between. In the gap between absorbing those few concentrated photons and emitting those many dilute photons, all the magnificent complexity of the biosphere does its work. Plants capture the low-entropy sunlight and use it to build sugars, concentrating carbon and hydrogen into ordered molecular structures. Animals eat the plants and use the chemical energy in those sugars to move, grow, think, and maintain their body temperature. Bigger animals eat smaller animals. Decomposers break down what's left, and at every step, energy is degraded, entropy increases, and waste heat is radiated into the environment and eventually into space. Life on Earth is a processing system. It takes in low-entropy energy, does interesting and complex things with it, and excretes high-entropy waste. We are, in the most literal thermodynamic sense, entropy machines. We accelerate the dispersal of energy. We take concentrated sunlight and spread it out faster than rocks and oceans alone would. And here is the profound part. Some scientists have suggested that life itself might be a consequence of the second prohibition, not just compatible with increasing entropy, but actually driven by it. Jeremy England, a physicist, has proposed that if there is a constant stream of concentrated energy hitting a collection of atoms, the second law favors the emergence of structures that are good at dissipating that energy.
Structures that absorb energy efficiently and spread it out effectively are thermodynamically favored over structures that don't, and over time, given enough energy and enough atoms, these structures become more and more complex, more and more efficient at entropy production. England speculates that this process, given enough time, could lead to something that looks an awful lot like life. In his own words, you start with a random clump of atoms, and if you shine light on it for long enough, it should not be so surprising that you get a plant. Now, this is a hypothesis, not an established theory. The details are debated, and there is much we don't understand about the origin of life. But the basic thermodynamic insight is sound. Life doesn't violate the second law. Life exemplifies it. Living things are extraordinarily good at taking concentrated energy and spreading it out, and the biosphere as a whole produces far more entropy than a lifeless Earth would.
Measurements show that the surface layer of seawater produces between 30 and 680% more entropy when cyanobacteria and other organic matter are present than when it's not. So the prohibitions don't just allow complexity, they may actively promote it. The walls of the maze don't just constrain the path, they create it. Think about a river. A river exists because of gravity, which pulls water downhill, and because of the landscape, which channels the flow. Without gravity, the water would sit there, motionless. Without the landscape, the water would spread out in a uniform sheet, equally dull. But with both, with the driving force and the constraints, you get something beautiful. Meanders, rapids, waterfalls, deltas, whole ecosystems thriving in the channels that the constraints create. The four prohibitions of thermodynamics are the landscape, and the flow of energy through the universe is the water.
The prohibitions channel the flow, constrain it, direct it, and in doing so, create the conditions for complexity and beauty and life. Without the prohibitions, the energy would just sit there, uniform and featureless, or it would spread out instantly, without ever passing through the exquisite middle stages where interesting things happen. Because here's a detail about entropy that is easy to miss. Both very low entropy and very high entropy are simple. A perfectly ordered crystal at absolute zero is simple. A uniform, featureless gas at thermal equilibrium is simple. Complexity lives in the middle, in the transition zone, in the region between order and chaos, between the beginning and the end, between the low entropy past and the high entropy future. There is a beautiful image for this. Imagine a cup of black tea and a small pitcher of milk. The tea alone is simple, uniform, dark. If you pour the milk in and stir thoroughly, the result is simple too, a uniform, pale brown. But in the moment of pouring, as the milk first enters the tea, swirling and curling, forming delicate tendrils and spirals and clouds, in that brief, transient moment, the complexity is stunning. Beautiful structures emerge, exist for an instant, and dissolve. The universe is in that moment. We are in that moment. The entropy was low at the beginning, in the smooth, uniform aftermath of the Big Bang. It will be high at the end, in the featureless, lukewarm equilibrium of heat death, trillions upon trillions of years from now. And right now, in between, the entropy is increasing. The milk is mixing with the tea, and we are the swirls.
We are the fleeting, beautiful, transient structures that emerge when energy flows from concentrated to dispersed, when entropy increases, when the universe moves from its improbable beginning toward its probable end. The prohibitions make all of this possible. The first prohibition ensures the energy is there to work with. The second ensures it flows in a direction, creating the arrow of time, the difference between past and future, the possibility of history and memory and cause and effect. The third ensures the process never fully stops, that the game goes on, that there is always a bit further to go, a bit more complexity to create, a bit more structure to emerge before the final, distant equilibrium. And the zeroth prohibition, the quiet foundation, ensures that temperature is real, that equilibrium is well defined, that the whole framework rests on solid ground. 4 prohibitions, 4 walls, and between them, everything that exists. Josiah Willard Gibbs was an American physicist, born in 1839 in New Haven, Connecticut. He spent virtually his entire career at Yale, where he was a professor of mathematical physics. He was quiet, modest, and famously reclusive. He never married. He lived with his sister. He published most of his important work in an obscure journal, The Transactions of the Connecticut Academy of Arts and Sciences, where it was read by almost nobody in America. His reputation grew primarily in Europe, where scientists like Maxwell and Boltzmann recognized the extraordinary depth of his work. Gibbs's great contribution was to combine the first and second laws into a single framework that could predict whether a process would happen spontaneously. And the key quantity in that framework is what we now call Gibbs free energy, written as G. Here is the problem Gibbs was solving. You know from the second law that spontaneous processes increase the total entropy of the universe. Universe meaning system plus surroundings. If you want to know whether a reaction will happen on its own, you could, in principle, calculate the entropy change of the system, then calculate the entropy change of the surroundings, add them up, and check whether the total is positive. If it is, the reaction is spontaneous. If it isn't, the reaction won't happen on its own. But calculating the entropy change of the surroundings is inconvenient. The surroundings are huge. They're the entire rest of the universe. You don't want to have to think about the entire rest of the universe every time you want to know whether a reaction will go forward. What you want is a criterion that involves only the system, quantities you can measure right there in your beaker or your reactor, without worrying about the rest of the world. Gibbs found such a criterion. He defined a new quantity, G equals H minus Ts, where H is the enthalpy, T is the absolute temperature, and S is the entropy of the system. The change in G for a process at constant temperature and pressure is delta G equals delta H minus T delta S. And the criterion for spontaneity is beautifully simple. If delta G is negative, the process is spontaneous. If delta G is positive, the process is not spontaneous and will not happen on its own. If delta G is 0, the system is at equilibrium. That's it. One number, one sign, one answer. Will this reaction happen or won't it? The genius of the Gibbs free energy is that it folds the entropy change of the surroundings into a quantity you can calculate from the system alone. When a reaction releases heat, when delta H is negative, that heat flows into the surroundings and increases their entropy. The T delta S term in the Gibbs equation accounts for the entropy change of the system itself, and the balance between them, delta H minus T delta S, captures the total entropy change of the universe, repackaged into a criterion that only requires you to know what's happening inside your system. Let me unpack this with an example that makes the interplay clear. Consider ice melting at room temperature. The system is the ice. When ice melts, it absorbs heat from the surroundings. Delta H is positive because the system is gaining energy. The surroundings cool down slightly, losing entropy. If you looked only at the enthalpy, at the fact that the system is absorbing energy, you might think this process should not be spontaneous. Why would the surroundings voluntarily give up energy? But there is another factor. When ice melts, the molecules go from a rigid, ordered crystal lattice to a fluid, disordered liquid. The entropy of the system increases significantly. Delta S is positive and large, and at room temperature, the T delta S term, the entropy contribution, outweighs the delta H term, the enthalpy contribution. Delta G is negative. The process is spontaneous. Ice melts at room temperature because the entropy gain of the system more than compensates for the energy cost. Now consider the same process at minus 20 degrees Celsius. The enthalpy of melting hasn't changed. The entropy of melting hasn't changed much either. But T is lower, so the T delta S term is smaller. At minus 20, delta H is larger than T delta S. Delta G is positive. The process is not spontaneous. Ice does not melt at minus 20 degrees. It stays solid, and at exactly 0 degrees Celsius at the melting point, delta G equals 0. The system is at equilibrium. Ice and water coexist. Neither phase is growing at the expense of the other. The melting point is the temperature at which the enthalpy and entropy contributions exactly balance. This is why substances have specific melting points and boiling points. The transition temperature is where delta G switches from positive to negative, where the entropic drive to change state exactly balances the enthalpic cost. Below that temperature, the ordered phase is favored. Above it, the disordered phase is favored. At the transition itself, both phases are in equilibrium. Gibbs free energy brings together all 4 prohibitions into a single working tool. The first prohibition guarantees that energy is conserved, which makes enthalpy meaningful. The second prohibition provides the entropy, the directionality, the arrow. The third prohibition gives a reference point for entropy, anchoring the calculations. And the zeroth prohibition ensures that temperature is well defined, so the T in the formula actually means something. Without any one of the 4 prohibitions, the Gibbs free energy wouldn't work. It is the place where all 4 walls meet. Now, I want to spend some time here making sure the language of thermodynamics is clear, because one of the reasons this subject has a reputation for being confusing is that the terminology can feel like a foreign language, and the same words sometimes mean different things in different contexts. If you've ever tried to read a thermodynamics textbook and felt lost, it probably wasn't because the ideas were beyond you, it was because the vocabulary was getting in the way.
So let's walk through the key terms, slowly, and make sure each one is anchored to something concrete. A system is whatever you're studying. That's it. If you're studying a gas in the cylinder, the gas is your system. If you're studying a cup of coffee, the coffee is your system. If you're studying a chemical reaction happening in a beaker, the contents of the beaker are your system. The system is whatever you've drawn a mental boundary around, the thing you're focusing your attention on. The surroundings are everything else. The room around the coffee, the air outside the cylinder, the table the beaker is sitting on. In principle, the surroundings extend to the rest of the universe, but in practice, you only care about the parts of the surroundings that interact with your system. The boundary is what separates the system from the surroundings. Sometimes it's a physical wall, like the walls of a container. Sometimes it's imaginary, a conceptual line you draw for the purpose of analysis. And the type of boundary determines the type of system. If the boundary allows both energy and matter to pass through, you have an open system. A pot of boiling water with no lid is an open system because steam escapes carrying mass away, and heat radiates into the kitchen. If the boundary allows energy but not matter to pass through, you have a closed system. A sealed pressure cooker on a stove is close to a closed system because heat enters through the walls, but the contents stay inside. If the boundary allows neither energy nor matter to pass through, you have an isolated system. A perfect thermos flask would be an isolated system.
though in reality, no thermos is perfect. Some heat always leaks. The state of a system is described by its properties. For a gas, the key properties are pressure, volume, temperature, and the number of moles. If you know these properties, you know the state. And here is a crucial distinction that catches many people. Some properties are state functions, and some are not. A state function is a property whose value depends only on the current state of the system, not on how the system got to that state. Temperature is a state function. Pressure is a state function. Volume, internal energy, enthalpy, entropy, all state functions. If you know where you are, you know the value of every state function. It doesn't matter how you got there. Heat and work, on the other hand, are not state functions. They are path functions. The amount of heat transferred to a system depends on the path, on the specific process used to get from one state to another. The amount of work done depends on the path too. You can take a gas from state A to state B by many different routes, heating it at constant pressure, or compressing it at constant temperature, or some combination, and the heat and work will be different for each route. But the change in internal energy, delta U, will be the same for all of them, because internal energy is a state function. This is actually a deep consequence of the first law. Delta U equals Q plus W. The left side is a state function, but the right side is the sum of two path functions. Different paths give different Q and different W, but their sum, the change in internal energy, is always the same. The books always balance, regardless of the route. There is an analogy that helps here. Think about altitude. If you hike from the bottom of a mountain to the top, your change in altitude is a fixed number, say 3,000 feet. It doesn't matter whether you took the gentle switchback trail or the steep scramble up the rock face. The altitude at the bottom is the altitude at the bottom, and the altitude at the top is the altitude at the top. The change is always the same. Altitude is like a state function. But the distance you walked is not a state function. The switchback trail might be 10 miles. The scramble might be 2. The distance depends on the path. Distance is like heat or work. Now, let's talk about the different kinds of processes because these show up everywhere in thermodynamics and they're essential for solving problems. An isothermal process is one where the temperature stays constant. Iso means same, thermal means temperature. If you expand a gas slowly while keeping it in contact with a large heat reservoir that maintains its temperature, that's isothermal. The gas does work by expanding, and it absorbs heat from the reservoir to replace the energy it spent. The temperature doesn't change. For an ideal gas, since internal energy depends only on temperature, the internal energy doesn't change either, and all the heat absorbed goes directly into the work done by the gas. An adiabatic process is one where no heat is exchanged between the system and the surroundings. The word adiabatic comes from the Greek for impassable, and it means the boundary is perfectly insulating. No heat in, no heat out. If a gas expands adiabatically, it does work, and since no heat is entering to replace the spent energy, the temperature drops. The gas cools itself by expanding. This is actually how many refrigeration cycles work at the molecular level. It's also why the air gets colder as you go up a mountain. Air rising in the atmosphere expands because the pressure decreases with altitude, and that expansion is roughly adiabatic, so the air cools. An isochoric process, sometimes called isovolumetric, is one where the volume stays constant. Iso means same. Choric comes from the Greek for space or volume. If you heat a gas in a rigid, sealed container, the volume can't change, so no pressure volume work is done. All the heat goes into increasing the internal energy and raising the temperature. An isobaric process is one where the pressure stays constant. Iso means same. Baric means pressure. If you heat a gas in the cylinder with a freely moving piston, and the piston is exposed to constant atmospheric pressure, the gas expands at constant pressure. Some of the heat goes into work, pushing the piston outward, and the rest goes into increasing the internal energy. Each of these processes traces a different path on a pressure-volume diagram, and the area under that path represents the work done. This is worth sitting with for a moment, because it connects the abstract mathematics to something visual. On a PV diagram, pressure is on the vertical axis and volume is on the horizontal axis. If a gas expands from volume V1 to volume V2, the work done by the gas is the area under the curve on the PV diagram between V1 and V2. For an isobaric process, the curve is a horizontal line and the area is a rectangle, pressure times change in volume. For an isothermal process, the curve is a hyperbola, and the area under it is given by the natural logarithm formula that we can derive from the ideal gas law. For an adiabatic process, the curve is steeper than the isothermal one, falling off more sharply because the gas cools as it expands and the pressure drops faster. Understanding these different processes and being able to calculate the heat, work, and internal energy change for each one is really the core skill of basic thermodynamics. And the first law, delta U equals Q plus W, is the tool that ties it all together. Let me also mention enthalpy, because it comes up constantly, and people sometimes confuse it with internal energy. Enthalpy, which we write as H, is defined as H equals U plus PV. It is the internal energy plus the product of pressure and volume. At first glance, this seems like an arbitrary combination. Why would you add PV to the internal energy? The answer is purely practical. In chemistry, most reactions happen at constant pressure because most reactions happen in open containers on lab benches where the atmospheric pressure is constant. When a reaction happens at constant pressure, the heat absorbed or released by the reaction equals the change in enthalpy, not the change in internal energy. Delta H equals Q at constant pressure. This is incredibly convenient because it means you can measure the heat of a reaction simply by measuring the temperature change in a calorimeter at constant pressure, and that gives you delta H directly. You don't need to worry about the work done by expanding gases separately. The enthalpy handles it for you. Enthalpy is a state function, just like internal energy. Its value depends only on the state of the system, not on how you got there. And the change in enthalpy for a reaction, delta H, tells you whether the reaction releases heat, in which case delta H is negative and the reaction is called exothermic, or absorbs heat, in which case delta H is positive and the reaction is called endothermic. There is a beautiful law about enthalpy that was discovered by a Russian-Swiss chemist named Germain-Henri Hess in 1840, even before the first law of thermodynamics was formally stated. Hess's law says that the total enthalpy change for a reaction depends only on the initial and final states of the reactants and products, not on the intermediate steps. If you can get from A to B directly, or by going from A to C and then from C to B, the total delta H is the same. This is a direct consequence of enthalpy being a state function. The path doesn't matter. Only the end points matter. Hess's law is extraordinarily useful in chemistry because it means you can calculate the enthalpy change for reactions that are difficult or impossible to carry out directly by combining the enthalpy changes of reactions that are easy to measure. It is also the foundation for using standard enthalpies of formation, tabulated values that tell you the enthalpy change when 1 mole of a compound is formed from its constituent elements in their standard states. With a table of formation enthalpies, you can calculate the enthalpy change for virtually any reaction. And all of this, every bit of it, rests on the prohibitions. The first prohibition guarantees that energy is conserved, which makes the bookkeeping possible. The second prohibition tells you which direction reactions will go spontaneously, which we quantify using a combination of enthalpy and entropy called Gibbs free energy. The zeroth prohibition guarantees that temperature is well defined, which makes calorimetry meaningful. And the third prohibition gives you an absolute reference point for entropy, which lets you calculate whether a reaction is spontaneous at any temperature. The prohibitions aren't just abstract principles, they are the working tools of every chemist and every engineer who deals with energy, heat, and reactions. They are the grammar of the language of change. Let me bring everything together with a single detailed example that shows all four prohibitions cooperating. Consider a simple process that happens billions of times a day all over the world. Boiling water on a stove. You place a pot of water on a gas burner. The gas burns, releasing chemical energy as heat. That heat flows through the metal bottom of the pot and into the water. The water temperature rises. Eventually, at 100 degrees Celsius, at standard atmospheric pressure, the water begins to boil. Liquid water transforms into steam. The steam rises off the surface and disperses into the kitchen air. Now watch how the four prohibitions govern every aspect of this process. The zeroth prohibition is at work the moment the flame touches the pot. The flame is hotter than the pot bottom. The pot bottom is hotter than the water at the bottom of the pot. The water at the bottom is hotter than the water at the top. Heat flows through a chain of thermal contacts, from flame to metal to water, always from hotter to cooler, always toward equilibrium. The thermometer you dip into the water gives a reading that is consistent and meaningful, because the zeroth prohibition guarantees the transitivity of thermal equilibrium. The temperature the thermometer reads is the same temperature that every other properly calibrated thermometer would read. Temperature is real, consistent, and trustworthy. The first prohibition governs the energy accounting. The chemical energy released by burning the gas equals the heat transferred to the water, plus the heat lost to the surrounding air, plus the heat that warms the pot itself, plus the light emitted by the flame. Nothing is created, nothing is destroyed. The books balance. And the heat that enters the water goes into two things: raising the water's temperature, which is increasing its internal energy, and at the boiling point converting liquid water into steam, which is doing the work of expanding the water's volume by a factor of about 1600 as it changes from liquid to gas. Delta U equals Q plus W, always. The second prohibition governs the direction and the inevitability of every step. Heat flows from the flame to the water, never the reverse. The entropy of the universe increases at every stage. The concentrated chemical energy in the gas, low entropy, is converted into dispersed thermal energy in the water, the pot, and the air, higher entropy.
When the water boils, the steam disperses into the room, carrying energy with it, spreading it out, increasing the entropy further. You cannot reverse this process spontaneously. You cannot gather the dispersed steam from the kitchen, condense it back into the pot, reassemble the chemical bonds in the exhaust gases, and restore the natural gas to its original state. The second prohibition forbids it. The process is irreversible. And the third prohibition lurks in the background, setting the absolute temperature scale that makes the efficiency calculations meaningful, establishing the reference point for entropy that allows us to calculate delta G for the vaporization, and guaranteeing that you can never cool anything all the way to absolute zero, which means there will always be some thermal energy, always some molecular motion, always some entropy to work with. A pot of boiling water, the simplest, most mundane kitchen activity imaginable. And the entire framework of thermodynamics, all four prohibitions, every concept we've discussed tonight, from Carnot's ideal engine to Boltzmann's formula to Gibbs free energy, is operating right there, in that pot, on that stove, every single time you make a cup of tea. And that, I think, is what makes thermodynamics so remarkable. These aren't abstract principles relevant only in laboratories and power plants.
They are the operating system of reality. They govern everything. The cooling of your coffee, the beating of your heart, the shining of the stars, the arrow of time itself. 4 prohibitions, worked out over a century by a scattered handful of brilliant, often tragic individuals, and confirmed by every experiment, every observation, every measurement ever made. The universe has rules. You are living inside them. And tonight, as you lie there, the rules are working perfectly, silently, effortlessly, keeping the energy flowing, keeping the entropy climbing, keeping the temperature well-defined, keeping the absolute zero unreachable, keeping the world turning. There is nothing you need to do. There is nothing you need to manage. The prohibitions handle it. They have been handling it since the first fraction of a second after the Big Bang, and they will continue handling it until the last whisper of energy disperses into the silence of an empty, cooling cosmos. But tonight, the cosmos is not empty. Tonight, it is full of warmth and motion and complexity and life. Tonight, the milk is still swirling in the tea, and you are here to see it. Rest well. The 4 prohibitions are keeping watch. Let me take you on one more journey tonight before we wind down. Because the prohibitions don't just govern coffee cups and steam engines. They govern stars. They govern galaxies. They govern the birth, evolution, and eventual death of the universe itself. Right after the Big Bang, roughly 13.8 billion years ago, the universe was in an extraordinarily low entropy state. Now, this might seem counterintuitive, because the early universe was a hot, dense, nearly uniform soup of particles and radiation. Everything was mixed. The temperature was basically the same everywhere, varying by at most a tiny fraction of a percent. That sounds like a high entropy state, doesn't it? Everything spread out, everything uniform. But there is something we haven't accounted for, and it changes everything. Gravity. Gravity is the odd one out in thermodynamics. For most systems, the equilibrium state, the state of highest entropy, is the one where everything is uniformly spread out. But for a system dominated by gravity, the opposite is true. Gravity pulls matter together. A uniform distribution of matter under gravity is actually a very low entropy state, because gravity wants to clump it. The high entropy state for a gravitational system is one where matter is concentrated into dense lumps, like stars and black holes, with vast empty spaces between them. So the smooth, uniform early universe, which looks like a high entropy state if you ignore gravity, is actually a spectacularly low entropy state once you include it. All that matter, all that energy, spread out uniformly, when gravity desperately wants to pull it together. The universe began in an improbable configuration, and it has been moving toward more probable ones ever since. Over billions of years, matter clumped together under gravity. Clouds of gas collapsed into stars. Stars clustered into galaxies. At each step, gravitational potential energy was converted into kinetic energy, into radiation, into heat. Entropy increased. And the structures that formed, the stars, the planets, the galaxies, were products of that increase. They are way stations on the road from low entropy to high entropy, structures that emerge during the transition, like the swirls of milk in tea. Stars burn for billions of years, converting hydrogen into helium, releasing enormous amounts of energy as light and heat. That light, that low entropy concentrated radiation, is what fuels life on planets like Earth. When a star exhausts its fuel, it collapses. The most massive stars collapse into black holes. And black holes, it turns out, are the universe's greatest reservoirs of entropy. In 1972, a physicist named Jacob Bekenstein proposed that black holes have entropy, and that the entropy is proportional to the surface area of the black hole's event horizon. This was a startling claim, because it connected gravity, quantum mechanics, and thermodynamics in a way nobody had anticipated. Stephen Hawking initially thought Bekenstein was wrong and set out to prove it. But to his own surprise, his calculations showed that black holes do indeed have a temperature. They do emit radiation, now called Hawking radiation, and they do have entropy, and it is enormous. The supermassive black hole at the center of the Milky Way has about 10 to the 91 Boltzmann constants of entropy. That is 1,000 times as much as the entire observable universe had right after the Big Bang. And all the black holes in the universe together account for the overwhelming majority of the universe's total entropy. So, the flow of entropy in the universe goes something like this. It started low, in the smooth, uniform conditions after the Big Bang. Gravity pulled matter together, forming stars and galaxies, increasing entropy. Stars burned, radiating light, increasing entropy further. The most massive stars collapsed into black holes, which contain stupendous amounts of entropy. And the black holes themselves, over unimaginably long timescales, slowly evaporate through Hawking radiation, spreading their energy and entropy into the surrounding space. In the very distant future, long after the last star has burned out, long after the last black hole has evaporated, the universe will approach its final state, a diffuse, uniform, lukewarm bath of low-energy photons, slowly cooling, slowly spreading, with nothing left to drive any process, no temperature differences, no energy gradients, no potential for work. This is the heat death of the universe, the maximum entropy state, the end of the road. At that point, even on large scales, you would not be able to tell the difference between time moving forward and time moving backward. The arrow of time itself would dissolve. Because the arrow of time exists only as long as entropy is increasing, and when entropy has reached its maximum, there is nowhere left to go. But that is unimaginably far in the future. More than 10 to the 100 years from now. A number so large that writing it out would take more pages than exist in all the libraries on Earth. We don't need to worry about heat death tonight. What matters tonight is the middle. The rich, complex, beautiful middle, where entropy is increasing, where energy is flowing, where structures are forming and dissolving, where life is flourishing on the banks of the entropic river, sustained by the low entropy sunlight that our star so generously provides. We are here because the entropy was low, and it is increasing. We are the swirls in the tea. We are the transient, improbable, magnificent structures that emerge when the universe moves from order to chaos. And we exist precisely because that movement is happening. Not despite the second prohibition, but because of it. Let me take you back to the question we touched on earlier, because it deserves a full telling, and because it connects all 4 prohibitions to the most immediate fact of your daily existence. What does the Earth get from the Sun? Almost everyone, when asked this question, says energy. And that answer is technically correct, but deeply incomplete. Because the Earth also gives energy back. It radiates almost exactly as much energy into space as it receives from the Sun. If it didn't, the Earth would be heating up dramatically, and while the planet is warming somewhat due to the enhanced greenhouse effect, over geological timescales, the energy budget is very nearly balanced. Energy in roughly equals energy out. So if we're not keeping the energy, what is the Sun actually giving us? The answer, as we discussed, is low entropy. The Sun sends us energy in the form of a relatively small number of high-energy photons, visible light, ultraviolet, mostly photons with wavelengths in the range that our eyes can detect. Each one of these photons carries a significant amount of energy in a compact, concentrated package. This is low-entropy energy, ordered, concentrated, useful. The Earth absorbs those photons, and every process on Earth, from photosynthesis to weather to the digestion of your dinner, uses that energy and degrades it. By the time the Earth radiates the energy back into space, it has been converted into infrared radiation, a much larger number of much lower energy photons. For every single photon received from the Sun, the Earth emits roughly 20 photons. The total energy is the same, but it has been spread across 20 times as many carriers, each one individually much less energetic. The entropy has increased enormously. And all the magnificent complexity of life on Earth exists in the gap between the low entropy input and the high entropy output. We are the middlemen. We are the process that converts concentrated sunlight into dispersed infrared radiation. And in between, we do everything. We grow, we think, we build cities, we compose music, we lie in the dark and listen to stories about thermodynamics. This picture illuminates the second prohibition in a way that I find deeply satisfying. The second prohibition doesn't say that order can't exist. It says that local order must be paid for by global disorder. The Earth is more ordered, more complex, more structured than it would be without the Sun. But that local decrease in entropy is more than compensated by the massive increase in entropy from converting concentrated photons into dispersed ones. The total entropy of the Sun-Earth space system goes up, as the second prohibition demands. And the Sun itself is paying the same kind of price. The Sun's energy comes from nuclear fusion, where hydrogen nuclei are squeezed together to form helium. This process converts a tiny amount of mass into a large amount of energy, following Einstein's famous E equals mc squared. The mass of the Sun is slowly decreasing. The energy it radiates is slowly dispersing into the void. The Sun is burning through its low-entropy nuclear fuel, converting it into high-entropy radiation, and in the process, it provides the steady stream of concentrated energy that life on Earth depends on. And where did the Sun get its low-entropy fuel? From the gravitational collapse of a cloud of gas and dust, billions of years ago. That cloud was itself a product of even earlier processes, supernova explosions and stellar winds from earlier generations of stars. And those earlier stars formed from the gravitational clumping of matter in the young universe. And the young universe had extraordinarily low entropy because of the smooth, uniform distribution of matter under the influence of gravity. So the chain goes back, all the way back. The low entropy that sustains life on Earth today is, in a deep sense, borrowed from the Big Bang. The initial conditions of the universe, that smooth, hot, nearly uniform state that looks like maximum entropy, but is actually minimum entropy once you account for gravity, those initial conditions set the entire chain in motion. The gravitational clumping, the formation of stars, the nuclear fusion, the radiation of light, the photosynthesis, the food chains, the chemical reactions in your cells, all of it is one long cascade of entropy increase from the improbable beginning to the inevitable end. And everything interesting, everything structured, everything complex, everything alive exists in the middle of that cascade. Between the low entropy past and the high entropy future, between the Big Bang and the heat death, between the first photon and the last, we are the middle. We are the swirls in the tea. There is one last thread I want to follow before we close, because it ties together everything we've discussed and addresses what might be the deepest question thermodynamics raises. Why can't you unscramble an egg? You can scramble one easily enough. Crack the shell, whisk the contents, pour them into a hot pan. The proteins denature, the liquids solidify, and you have scrambled eggs. Now try to reverse it. Take the scrambled eggs and turn them back into a raw egg, with a clear white and an intact yolk, sitting neatly inside a reassembled shell. You can't. Nobody can. And yet, the first prohibition says energy is conserved. Every atom that was in the raw egg is still in the scrambled egg. No energy has been created or destroyed. In principle, every molecular process that happened during scrambling, every protein unfolding, every bond breaking, every bond forming is individually reversible at the molecular level. The fundamental laws of physics that govern individual molecular interactions work just as well backward as forward. So why can't you unscramble the egg? Because the second prohibition says so. The number of microscopic configurations corresponding to scrambled egg is incomprehensibly larger than the number corresponding to raw egg. Moving from raw to scrambled is like shuffling a deck of cards. Virtually any shuffle takes you further from a sorted deck. Moving from scrambled to raw would require every atom, every molecule, every protein to simultaneously and spontaneously arrange itself into exactly the right configuration, and the probability of that happening is so astronomically small that it will never occur in the observable lifetime of the universe. The irreversibility is not in the laws. The laws are symmetric. The irreversibility is in the statistics. It is in the overwhelming preponderance of disordered states over ordered ones. It is in the simple, brutal arithmetic of large numbers. And this is why time has a direction. The fundamental equations of physics don't distinguish past from future. An electron orbiting a nucleus looks the same whether you run the film forward or backward. A ball bouncing off a wall looks the same in both directions. But a glass shattering on the floor does not look the same in reverse. An ice cube melting in a warm drink does not look the same in reverse. A living thing aging and dying does not look the same in reverse. The direction comes from entropy. The past is the direction of lower entropy. The future is the direction of higher entropy. And the fact that we remember the past but not the future, the fact that causes precede effects, the fact that time feels like it moves in one direction, all of this is rooted in the second prohibition. In the statistical tendency of energy to spread out, in the simple fact that there are overwhelmingly more disordered arrangements than ordered ones. If the universe had started in a state of maximum entropy, of perfect equilibrium, there would be no arrow of time. Nothing would happen. Nothing could happen. Every direction in time would be equivalent. The universe would be static, featureless, dead. But the universe did not start that way. It started in an extraordinarily low entropy state, and everything that has happened since, every star, every planet, every rainstorm, every heartbeat, every thought, has been part of the long, slow, majestic slide from that improbable beginning toward the most probable end. We are passengers on the entropic current, carried forward by the universal tendency toward dispersal, sustained by the pockets of low entropy that stars and planets and living things create along the way. And the four prohibitions are the riverbanks. They shape the current. They define what is possible and what is forbidden. They create the channels through which energy flows and complexity emerges. Without them, there would be no river. Without them, there would be no us. Right now, your body is obeying all four. Your cells are maintaining their internal order, their exquisite molecular machinery, by consuming low-entropy food and excreting high-entropy waste. Your heart is pumping blood, converting chemical energy into mechanical work, with waste heat radiating from your skin. Your brain is processing information, creating and erasing memories, and every erasure, as Landauer showed, generates a tiny bit of entropy. You are a thermodynamic masterpiece, a cathedral of organized complexity, sustained by the constant flow of energy from ordered to disordered, from concentrated to dispersed, from low entropy to high. And tonight, as you drift towards sleep, that flow continues. Your metabolism slows, your body temperature drops slightly, your breathing becomes regular and deep. The chemical reactions in your cells continue, converting glucose into carbon dioxide and water, releasing energy that keeps your organs functioning and your body warm. The entropy of the universe increases, imperceptibly, with every breath you take. The prohibitions keep watch through the night. They have kept watch since the beginning. They will keep watch until the end, whenever and however that end may come. In the unimaginably distant future, when the last black hole evaporates and the last photon drifts through an empty, cooling universe, carrying the last whisper of the low entropy past into the silence of maximum entropy. But that is so far away. Tonight is here, and tonight the four walls still stand, and between them the world still turns, and the energy still flows, and you are still warm, and you are still breathing, and you are still wonderfully, improbably, magnificently alive. So just breathe. Let the systems run. Let the entropy climb. Let the prohibitions do their work. They've been at it for 13.8 billion years, and they haven't made a mistake yet. Good night. The universe will still be following its rules in the morning. So here we are. We've walked through the whole thing, from the steam engines of 18th century Britain to the heat death of the universe, from Newcomen's nodding beam to Boltzmann's gravestone, from a 17-year-old boy writing to Napoleon to the supermassive black hole at the center of our galaxy. 4 prohibitions, 4 walls, and between them, everything. The zeroth prohibition says you must reach equilibrium, temperature must be consistent, the universe plays no favorites. The first prohibition says you can never create or destroy energy. The books always balance, you cannot win. The second prohibition says, in every real process some useful energy is lost, spread out, degraded. You cannot even break even. The third prohibition says, you can never reach absolute zero. The bottom is unreachable. You cannot quit the game. And the 4 together say something more than any one of them says alone.
They say that the universe is a system with a past and a future, an arrow and a direction, a beginning of exquisite improbability and an end of featureless uniformity, and a long, long middle, our middle, where the energy flows and the entropy climbs, and the structures bloom and fade like flowers in a cosmic spring. Right now, as you're lying there, all 4 prohibitions are at work. Your body is converting chemical energy into heat, obeying the first prohibition. That heat is radiating into the room, spreading out, increasing entropy, obeying the second. The room will never quite reach absolute zero, obeying the third. And your body and the room are approaching thermal equilibrium, your skin temperature slowly converging with the air temperature, obeying the zeroth. You are a thermodynamic system, a spectacularly complex, exquisitely organized, beautifully improbable thermodynamic system sustained by the low-entropy food you ate today, which got its energy from the low-entropy sunlight that fell on the plants or the animals that ate the plants. You are a link in a chain of energy transformations that stretches back to the nuclear furnace at the heart of the sun and further back to the gravitational collapse that formed the sun from a cloud of gas and further back still to the smooth, low-entropy initial conditions of the Big Bang itself. Every breath you take moves the universe a tiny bit closer to equilibrium. Every heartbeat increases the total entropy of the cosmos by an infinitesimal amount. And that is not a cause for sadness, it is the price of existence. Without the flow of entropy, without the constant movement from order toward disorder, there would be no motion, no change, no warmth, no cold, no sensation, no thought. The second prohibition is not your enemy. It is the current in the river of time, and you are riding it. The scientists who figured all of this out, Carnot, dying at 36 with his papers burned, Mayer, broken by rejection and grief, Joule, painstaking and patient in his brewery, Clausius, quiet and methodical, giving entropy its name, Boltzmann, passionate and tormented, his formula carved on his tombstone, Nernst, precise and formidable, setting the final boundary. They spent their lives reading the universe's rule book, and what they found was not a set of arbitrary restrictions. What they found was the grammar of reality.
The rules that make the universe a story rather than a static picture. The prohibitions that create the arrow of time, the flow of energy, the emergence of structure, and the possibility of life. You don't need to remember the formulas tonight. You don't need to remember the dates or the names. The prohibitions are working right now, whether you think about them or not. The way gravity works, whether or not you know Newton's equations. They are holding you on the surface of the Earth, keeping your blood flowing, keeping your neurons firing, keeping the stars burning, keeping the universe moving forward through time. So let that thought settle. The universe has 4 rules about what is allowed and what is not. And those 4 rules, those 4 walls, are the reason anything exists at all. They are the reason you exist. They are the reason tonight exists. They are the reason there is a difference between now and then, between here and there, between you and the room around you. And right now, in this particular moment, the entropy is just right. The energy is flowing at just the right rate. The structures are exactly as complex as they need to be. Your body knows how to convert food into warmth and thought. Your lungs know how to extract oxygen from the air. Your heart knows how to pump blood through 60,000 miles of vessels. All of it thermodynamics. All of it, the 4 prohibitions, working silently, perfectly, without pause. You don't have to manage any of it. You don't have to supervise the entropy. You don't have to enforce the conservation of energy. The prohibitions handle it. They always have. They always will. So let your thoughts soften. Let the concepts drift. Let the names and the formulas and the history settle into whatever corners of your mind want to hold them. The universe is following its rules tonight, as it does every night, as it has since the beginning, as it will until the last photon fades into the silence of maximum entropy. So far in the future that the number itself is almost meaningless. But that silence is unimaginably distant. Tonight there is warmth, there is motion, there is complexity and beauty, and the quiet hum of a universe playing by its own rules. Rest easy. The prohibitions are keeping watch.